The universe seldom announces its wonders with thunder. More often, it leaves a quiet trace, some faint shift in light, a filament of motion barely distinguishable from noise waiting for a mind on a small blue world to notice. And so it was with the strange ripple that would come to be associated with 3I divided by Atlas. Before it became a name spoken in observatories and mission rooms, before it stirred debate across the agencies and laboratories of Earth, it existed only as a wavering signature, a thin scar of photons sliding through a deep space scan meant to observe something else entirely. It passed unnoticed at first, a traveler disguised as statistical chance. But the universe has its own way of insisting on attention. On that quiet night, NASA's long-range detection grid, a mesh of orbiting observatories and Earth-based instruments intertwined by machine learning, was sweeping a region far beyond Neptune, calibrating for a survey of trans-Neptunian objects. Patterns it knew well flickered across its sensors: cold comets, dim dwarf planets, dust clouds ghosting in slow elliptic drifts. The sweep was routine, predictable, and then a tiny anomaly blinked a point of light, moving just slightly too quickly, slightly too smoothly, slightly too confidently across a span where interstellar darkness tends to soften trajectories into ambiguity. Even in that first instant, something about its demeanor felt foreign. NASA's systems flagged it twice, then a third time before submitting the signal to human review. The astronomers on duty approached the blip with caution. Interference happened. Sensor ghosts were common, yet the anomaly's persistence across multiple instruments carried a subtle gravity, a whisper that this was no internal artifact. There was something real here, something moving with a kind of deliberate consistency through territory where only the rarest cosmic wanderers passed. It did not match the thermal profile of typical Oort cloud objects, nor did it resemble an asteroid captured by the sun's outer gravitational fringe. Its motion cut cleanly, like a knife drawn across silk. As the scans deepened, the silhouette began to reveal a faint structure, an elongated glow tapering at both ends, reminiscent of the way a comet might appear if stripped of its coma and its chaotic debris. But there was no tail, no haze of sublimating ice, just a stark, sharp geometry gliding without hesitation through the cold. At this early stage, the team avoided speculation. The universe could deceive. It often did. Yet they noted the subtle rhythm in their own reactions, a rising curiosity, a sense of unease, a feeling that this fragment of light carried within it a secret waiting to unfurl. The memory of earlier interstellar arrivals, Oumuamua, that needle-shaped visitor of 2017, and the more volatile 2I divided by Borisov of 2019 still haunted cosmologists. Those two cosmic passers-by had opened the doorway to a staggering realization. The galaxy was not a closed room. The sun did not sit in isolation but along a galactic thoroughfare where travelers from unimaginable distances could and did wander through. But this one, this flicker that would be named 3I divided by Atlas, seemed different even from the beginning. Its light curve didn't fluctuate the way it should have if it tumbled irregularly. Its spectral reflections were too muted, too unified, as though the surface was smoother than a natural fragment had any right to be after untold eons drifting between stars. And its trajectory preliminary as the calculations were hinted at an approach not dictated solely by the sun's gravitational command. Something in its prior path suggested a long, straight cruise through interstellar void, unbent by encounters with rogue planets or stellar winds. It moved with an autonomy that felt almost serene. In mission rooms lit by blue monitors, the astronomers leaned closer. They watched frames replay, observed the path drawn against the black canvas of space, studied the energy distribution across wavelengths. They whispered to themselves, asked questions quietly into the dim. Was this merely another shard broken from a distant dying world? A relic of some star system far beyond the spiral arms? Or was it something stranger, an object formed under conditions unlike anything the solar system had ever produced? The deeper the scans reached, the more the faint unease turned to fascination. NASA's arrays refined their focus, layering more data upon what had first appeared as noise. As that data grew, the object's outline stabilized, revealing a slender, elongated profile with a reflective behavior inconsistent with icy comets. Not metallic, Not rocky, something in between, something composite and unknown. It glimmered in a way that felt almost crafted, though the thought was dismissed as premature imagination. Still, the question lingered. What kind of natural process could produce such a shape? Beyond the raw measurements, beyond the models being quietly compiled in draft form, there was a strange emotional undertow in the room, one shared by every person watching. It stemmed from the same ancient longing that humans had always carried, the desire to understand what lies outside the borders of the familiar. In the earliest days of oceanic exploration, that longing pointed toward the horizon. Now, it pointed toward preternatural shapes drifting through the void. The hook tightened when the object displayed a faint, rhythmic dimming, too subtle to be purposeful, yet too regular to be dismissed. It pulsed slowly as though breathing, though scientists resisted the allure of metaphor. Such rhythms could come from rotation, from albedo variations, from surface fissures reflecting starlight, and yet the pulse felt steady, elegant. Intentional or not, it carried a strange majesty. Within 24 hours, the scientific community knew that something extraordinary was entering the solar system again, and unlike previous visitors, 3I divided by Atlas arrived during a time when humanity had sharpened its tools, honed its detectors, and deployed a symphony of deep space scanners whose reach extended farther and finer than anything used in decades past. This time, humanity was prepared, if not to understand, then at least to witness with unprecedented clarity. But the universe is generous with beauty and stingy with answers. As the object's presence solidified in the data streams, something else began to emerge. Faint, perplexing signatures just beyond the primary readings. Reflections without source, shadows without bodies, shapes at the edges of detection that seemed to grow clearer the more doubts hardened. The scanners whispered of subtleties that defied immediate explanation, as though the anomaly was merely the outer shell of a deeper mystery. And so, the hook was set, not with spectacle, but with quiet inevitability. The object would continue inward, the scans would grow sharper, and the riddle that entered the solar system under the name 3I divided by Atlas would draw humanity into one of the most profound investigations in its scientific history, an inquiry not merely into what the object was, but into what strange stories interstellar space still held in its vast, unlit corridors. Naming has always been humanity's first act of control. When an unfamiliar light appears in the sky, it is given a label, an entry in a catalogue, a place in a hierarchy of objects. The process tends to be quiet, procedural, almost bureaucratic, yet behind these motions there is always a subtle drama. For what is being filed away is not just a point of light, but the unknown itself, pressed into human language. The strange visitor moved from being a curiosity on a monitor to a recognized object when its orbit was solved with enough precision to satisfy the guardians of nomenclature. Reports flowed from the survey network, measurements from multiple nights converging into numbers that could be fed into the equations of celestial mechanics. The orbital parameters told a clear story. The eccentricity was greater than 1, unmistakably hyperbolic. This was not a body circling the sun in some stretched ellipse. It was a traveler merely passing through, destined to slip back into interstellar space and never return. The designation came next. It followed a standardized pattern that hid the enormity of what it implied. The object was ordered in a growing list of interstellar visitors as the third such confirmed wanderer and attached to the survey that had first registered its presence. A line of letters and numbers, simple and clinical, marked it as 3I divided by Atlas. In that sparse sequence lay the acknowledgement that the solar system was again being visited from outside, by something that had formed beneath a foreign star or in the quiet depths between suns. Behind the formal tone of circulars and bulletins, the astonishment was difficult to conceal. Interstellar objects were supposed to be rare. For centuries, they were theoretical curiosities, imagined but unobserved. Then, within the span of a human lifetime, they began to appear, each one more unsettling than the last. The statistical models strained to reconcile such a frequency with expectations. It was as though the galaxy had decided to reveal a hidden river of debris, that had always been flowing past, just above the threshold of human awareness. Astronomers began to retrace the data trail that led to 3I divided by Atlas. They combed archives of sky surveys, examining the earliest frames where the object might have been hiding, faint and unnoticed. In each recovered exposure, it appeared as a slightly displaced point, just off where the background stars lay. The sequence, when stitched together, traced a steady passage inward, as if the object had been quietly approaching long before anyone thought to look in its direction. The motion, plotted against the slow drift of distant constellations, revealed a subtle peculiarity. The inbound trajectory was not aligned with the common plane where most planets and debris in the solar system reside. It cut across that great disk at a steep angle, an outsider slipping through a crowded room without obeying its invisible lanes. This inclination suggested an origin untied to the architecture of the sun's retinue. It came from a direction that, when projected backward, threaded through no known stellar nursery, no familiar cluster, no obvious birthplace. As the orbit was refined, an additional detail unsettled the analysts. The object's speed at great distance had been higher than typical for bodies simply dislodged from their home systems by gravitational interactions. There was nothing impossible in the numbers, nothing that violated the known limits of stellar dynamics. Yet the velocity sat at the outer edges of expectation, as though some rare, violent event had flung it out with more force than usual. The phrase that circulated quietly among modelers was simple. It should not be this common for objects like this to exist. The effort to classify its nature began almost as soon as its path was confirmed. Had it been a comet in its past, shedding ice and dust around some distant star, or a drying fragment of a planetesimal belt, hardened by cold and time into an inert shard, the light curve, as observations accumulated, refused to settle neatly into these categories. Its brightness did not rise in the way active comets did when warmed by sunlight. There were no obvious jets, no diffuse halos. Instead, it presented a rigid profile, its reflections oscillating in a pattern that hinted at an elongated shape with a surprisingly smooth exterior. Comparisons with earlier visitors were inevitable inside the minds of those studying it. The first confirmed interstellar wanderer had displayed non-gravitational accelerations and an inexplicable geometry that triggered years of debate. The second had behaved more like a textbook comet, a bridge between the familiar and the alien. Now this third arrival displayed characteristics that seemed to belong to neither lineage. It was not clearly an active comet, nor a typical asteroid, nor a mere repetition of previous enigmas. It was, instead, an object that sat at the margins of all these categories, as if testing the edges of human classification itself. In dedicated rooms where screens glowed in the dim, teams ran simulations, feeding in different densities, shapes, and compositions to see which combination could reproduce the observed light variations. The best fits required unlikely proportions, surfaces with low roughness, and a rotational state that defied easy comparison to known solar system objects. There was nothing overtly impossible in the parameters, yet it was as if nature were choosing a configuration that lay just beyond the comfort zone of experience. The phrase, "the object that should not exist," was never written in an official memorandum. Yet it appeared, scribbled in margins, whispered in hallways, shared in late-night conversations between colleagues who trusted one another enough to voice the feeling that the data stirred. It spoke not of violating physical laws, but of confronting a configuration of matter that seemed extravagantly unlikely. It hinted at the possibility that the processes shaping other planetary systems could sculpt outcomes entirely different from those familiar to the solar system. Perhaps even outcomes that mirrored intention in their precision. What made the situation feel even stranger was the timing. Humanity had only recently built instruments powerful enough, and algorithms attentive enough, to notice such faint drifters in the darkness. It was an age when deep learning combed through oceans of starlight, pulling out anomalies that human eyes would once have skipped over. In such a context, the arrival of another interstellar object might have been inevitable. Yet, this particular form, this particular brightness pattern, this particular orbit, combined to foster an impression that chance alone was stretching itself thin. The early scientific papers, careful in tone and measured in language, focused on probabilities and model fits. They detailed the anomalous aspects without dramatizing them. The numbers were presented as they were, stripped of emotion. Yet the underlying emotion remained, pulsing quietly beneath the equations. It was the recognition that the cosmos had once again placed an object inside humanity's reach that seemed to resist every easy attempt at explanation. In the silence between keystrokes and calculations, a quieter understanding emerged. If this object genuinely represented a form of matter that was rare, then it was a kind of message from the galaxy about its own diversity. A fragment of distant history had drifted into the local neighborhood, carrying with it clues about conditions that could not be recreated in any laboratory. It was as if the universe, indifferent and vast, had allowed one of its stranger creations to wander across the path of a species only just learning how to see. Thus, 3I divided by Atlas settled into the collective imagination of those who studied the sky, not as an impossibility, but as an indictment of assumptions. In its quiet, steady motion through the outer system, it suggested that what had been thought improbable might, in truth, be common, and that the catalogue of what can exist was still in its infancy. The story of discovery did not begin with a telescope pointed at a single star, but with rivers of data flowing continuously through distant antennas, mirrored servers, and restless algorithms. Night after night, the sky was being turned into numbers. Photons that had travelled for hours, or millennia struck detectors, were converted into digital counts and added to an ever-growing ocean of information. In that ocean, most waves were predictable. Stars rose and set. Known asteroids traced their arcs. Comets flared and faded. Yet hidden among these familiar patterns were occasional irregularities, tiny fractures in the symmetry that invited closer scrutiny. NASA had spent years weaving together a network of observatories designed to monitor the sky with relentless patience. Ground-based surveys scanned wide fields, cataloguing moving points against the tapestry of fixed stars. Space-based instruments, freed from the blur of atmosphere, pushed into fainter magnitudes, sensitive to whispers of light that would vanish before reaching any mountaintop. These instruments were linked not just by cables and radio, but by software architectures that allowed their data streams to merge into a single, evolving picture of the cosmos surrounding the solar system. At the heart of this system lived algorithms trained to recognize what the human eye would miss. They watched for small changes in brightness, for motions that subtly diverged from predicted paths, for repetitive features that hinted at unseen structure. Millions of detections, each a point of light on a digital frame, were constantly compared to catalogues. Most were quickly dismissed as known objects or artifacts. Only a fraction survived each filter, rising through tiers of increasingly focused analysis. On an unremarkable night, within this enormous mechanical awareness, a faint trace appeared in the outer regions of the monitored sky. It was not remarkable by itself, just a dim speck, slightly displaced between frames. Yet the systems around it were built to care about such details. Cross-correlation routines flagged the motion and marked it as a candidate track. The object persisted over multiple exposures, moving at a pace and direction that matched no known catalogue entry. A provisional identity was assigned. A new object had been seen. The long baseline nature of the scans meant that the sky was not simply glanced at, but continuously revisited. Wide fields overlapped. The same regions were captured at different times, under different conditions, with different instruments. By comparing these observations across hours and days, the motion of the new object could be traced with growing accuracy. Its path was not guessed. It was patiently extracted from the cumulative record, point by point. As new data poured in, automated systems began to estimate preliminary orbital parameters. These calculations were updated in real time, adjusting as each new position measurement refined the trajectory. At first, the orbit looked like that of a distant object, drifting at the frontier of the solar system. Then, as additional frames were incorporated, the calculated arc stretched outward, its curve flattening into a shape that did not close. The eccentricity began to creep above one, subtly at first, then decisively. A quiet tension ran through the monitoring software. Thresholds were being crossed. Flags that had rarely been triggered lit up in diagnostic logs. The object moved from the background queue of newly discovered trans-Neptunian bodies into a category reserved for candidates of interstellar origin. With that reclassification, its data stream was promoted for immediate human examination. In a dim monitoring room, a small team took control of the console. On their screens, the object appeared as a series of images, each with a faint point circled, the timestamp engraved in the corner. A separate display plotted its path against the star field, trailing a line that extended from the fringes inward. Another showed evolving estimates of its velocity and direction far from the sunday. The numbers suggested that, in the infinite distance, it had once drifted with a speed that could not be contained by any orbit. It was not bound, it was passing through. The observers did not rely solely on these visualizations. They dove into raw logs, checking for signs of instrumental anomalies. They verified that the source appeared consistently in different filters, different exposure times, different atmospheric conditions. The signature held. It was not a cosmic ray, not a reflection, not a software glitch. It was an object, solid and persistent, moving with purpose behind the curtain of noise. Meanwhile, the long baseline survey system continued its patient work. By comparing the new detections with historic data, it searched for earlier glimpses of the same object. Days, weeks, even months of past observations were sifted to find any trace that matched the extrapolated path. Slowly, a chain of faint detections emerged from the archive. Each recovered point added another bead to the thread of its trajectory, extending the known path and sharpening the estimate of its orbit. With each refinement, the hyperbolic nature of the orbit stood out more clearly. The total energy of the object with respect to the Sun was positive. No ordinary gravitational encounter within the system could have given it such an excess. The only reasonable conclusion was that it had arrived from the interstellar medium, carrying with it the dynamical memory of its distant origin. Alongside positional data, the system gathered information across different wavelengths, detectors sensitive to visible light, infrared, and near ultraviolet recorded its brightness. These measurements, once combined, allowed estimates of its surface reflectivity and approximate size. The numbers hinted at a body neither particularly massive nor especially faint. It was small by planetary standards, yet large enough to be an intact entity rather than a mere grain in the dust. The real power of the data streams, however, lay not only in brightness and position, but in the subtle variations between exposures. Tiny fluctuations in the observed light hinted at rotation. If one plotted brightness against time, a pattern began to form. Peaks and troughs appeared with a regularity that announced the object was spinning, presenting different cross-sections to the distant observers as it went. That modulation carried the first clues about its shape. Machine learning routines analyzed these light curves, comparing them to vast libraries of simulated objects with different geometries and spin states. The best matches suggested a highly elongated body, turning slowly, its length perhaps several times its width. The surface, judged by how its brightness changed with angle, appeared smoother than those of many comets or asteroids, with fewer abrupt features to scatter light erratically. The image this conjured in the minds of analysts was not of a jagged rock, but of something more streamlined. All of this unfolded without a single human eye ever looking directly at the object through a telescope eyepiece. Instead, the act of seeing was distributed across silicon and glass, code and fiber optics. Discovery had become a collective behavior, a partnership between instruments that never slept and minds that learned to interpret the traces they provided. The object existed, at first, only as a convergence of numbers, a structure emerging from patterns in data. As awareness of this presence spread through the network of observatories, the cadence of observations shifted. More telescopes were tasked with tracking it, each adding their own data stream to the global pool. High-priority alerts were circulated, encouraging other institutions to contribute follow-up measurements. The sky was big, and the window for close observation would not last forever. While the object was still relatively near, every available photon carried potential insight. The deep space scans that first revealed the visitor were never designed for a single spectacular event. They were built for patience, for accumulation, for the slow construction of knowledge from countless small observations. Yet every so often, This patient apparatus encountered something that concentrated its full capacity onto one narrow target. In such moments, the system resembled a great organism turning its many eyes toward a single point, curious and intent. Within that intent lay an unspoken realization. The galaxy was not a distant abstraction. It was a shared environment, a sea of material within which stars and planets moved together, exchanging fragments over incomprehensible distances and times. The data streams, so seemingly technical and dry, were in fact the sensory organs of a species beginning to feel its way in that sea, awakening to the presence of travelers that had once seemed imaginary. Once enough positional measurements had been collected, the motion could be lifted from raw coordinates into the language of orbits. The sky positions, each with its timestamp, were fed into solvers that translated dots on a star field into a path through three-dimensional space. At first glance, the result looked familiar. The object followed a sweeping arc, bending under the influence of the sun, curving inward and then outward again. The geometry resembled the classic hyperbolic swing of a visitor that arrives from interstellar distances, skims the inner system, and escapes once more into the dark. Yet details within that curve began to trouble the specialists in celestial mechanics. The shape of an orbit is never a simple line. It is a fragile compromise between gravity, inertia, and every subtle perturbation acting on a body. When the known forces are accounted for, the trajectory should settle into a solution that remains stable as more data pours in. The equations are unforgiving but reliable, their predictions honed through centuries of testing against planets, comets, and spacecraft. In this case, the predictions refused to stay fixed. Each new observation tightened the uncertainties, but instead of converging toward a single, consistent orbit, the computed path nudged itself away from the purely gravitational solution. Adjusted parameters could partially restore the fit, yet the residual discrepancies persisted like a low, insistent hum beneath the calculations. The object did not drift wildly. It behaved almost as expected, but not quite. The difference was small, comparable to the gentle push of sunlight, or a faint outgassing of vapor, and yet stubborn. Modelers turned their attention to non-gravitational forces. Many comets experience slight accelerations when volatile materials near their surfaces sublimate under solar heating. Invisible jets of gas and dust act like tiny thrusters, altering the orbit just enough to be measurable. These forces can be modeled if one knows something about the object's spin, shape, and activity. Standard formulations exist, refined by decades of observing icy bodies that flare as they approach the sunday. Those formulations were applied with care. Hypothetical jets were introduced into the equations, oriented along axes inferred from the light curve. The timing of solar illumination on different facets was computed to estimate when such outgassing should be most intense. The resulting accelerations were allowed to vary within plausible limits. Yet every attempt to reproduce the deviations in the trajectory ran into the same difficulty. The magnitude of the needed push did not match the signs of observable cometary behavior. The brightness remained too steady, too calm, for a vigorously active body. No obvious coma emerged, no diffuse tail swept out behind it. The object kept its crisp photometric profile, while the orbital fits demanded forces one would expect from a more visibly agitated traveler. To maintain consistency, one had to imagine jets that somehow provided significant thrust while leaving barely any trace in the scattered light. Alternative explanations were examined. Radiation pressure, the gentle momentum carried by photons themselves, can influence small, low-density objects with large surface areas relative to their mass. Solar sails, in theoretical designs, rely on this effect. If the interstellar body were extremely light for its size, perhaps a porous aggregate or a thin sheet, the sun's light could impart enough acceleration to account for the discrepancies. This hypothesis led to a different set of models. The density was lowered in simulations, the cross-sectional area increased. The trajectory was recalculated under these new assumptions. The fit improved in some regions of the path, aligning more cleanly with the recorded positions. Yet the implications felt uneasy. The implied material properties bordered on exotic, suggesting an object with a structure unlike any known fragment of rock or ice. A body that large, so low in density, would strain ordinary expectations about how such objects form and survive in the harsh environment between stars. To test the sensitivity of results, analysts perturbed the input conditions. They varied the assumed spin rate, the orientation of the rotation axis, the thermal properties of the surface. They accounted for tidal influences from planets, the subtle pull of the galaxy itself, and the drift of the solar system through the local interstellar medium. With each iteration, the orbital model bent itself toward the data, yet never quite relaxed into a simple, satisfying explanation. Something remained just slightly out of tune. Visualizations helped convey the strangeness. In simulated space, a cloud of test particles was released along trajectories consistent with natural ejection mechanisms from distant planetary systems. Stellar encounters, unstable resonances, and gravitational slingshots around giant planets were all considered as possible origin stories. These test particles, when propagated forward in time under realistic galactic dynamics, produced expected distributions of velocities and approach directions. Against this statistical backdrop, the actual path of 3I divided by Atlas stood out as uncommon, not impossible, not forbidden, but perched at the edge of the distribution. Its inbound speed, direction, and inclination combined into a signature that would be rare if only known ejection processes were at work. A few standard deviations separated it from the cluster of more typical outcomes. The phrase used in internal discussions was often simple and restrained. Low probability, but non-negligible. Still, the impression left in the minds of those running the simulations was more vivid. The object moved as if it carried a history that did not fit comfortably with the usual tales of chaotic scattering from protoplanetary disks. During virtual meetings, trajectories were displayed as ghostly arcs wrapping around the Sunday familiar paths of planets traced bright, closed loops. Known comets and asteroids populated thicker bands, forming a tangled skein of orbits within the ecliptic plane. The interstellar visitor cut across this architecture with cool indifference, an oblique line slicing through a web. At perihelion, its distance kept it well away from any planetary collision course, yet close enough for powerful telescopes to scrutinize. Once past that turning point, the arc extended outward again, lifting the object on a path that would soon carry it beyond the reach of detailed observation. For a time, some wondered whether unseen perturbations might be influencing the track. Could an encounter with a small, undetected body in the deep outer regions of the system have provided a subtle nudge? Could distributed gas or dust, more extensive than current models assumed, be imparting drag or lift? Extensive searches for such influences yielded nothing conclusive. No nearby masses large enough to matter were identified, and the interplanetary medium along the route did not appear dense enough to produce the measured effect. So attention returned, again and again, to the properties of the object itself. If its composition were unusual, its interaction with light and heat would be unusual as well. One speculative line of thought involved materials with extreme thermal responses, expanding or outgassing in ways that did not conform to conventional expectations. Another considered layered structures, where internal reservoirs of volatile substances might vent through narrow channels, producing directed jets that left only faint signatures at the surface. In quiet corners of the analysis, more daring possibilities were entertained. These discussions rarely appeared in formal reports, yet they had their own gravity. If the trajectory matched that of a body influenced by radiation pressure more than by mass, perhaps the object possessed structural properties closer to an engineered sheet or shell than to a solid rock. Under such conditions, the sun's light could steer it gently, like a breeze on an immense, delicate wing. The idea did not claim that the object was artificial, only that its behavior resembled scenarios long imagined for artificial craft. Even without such speculative layers, the path alone conveyed an unsettling beauty. In mathematical space, the orbit could be parameterized by a few constants, numbers that determined the shape and orientation of the curve. Yet behind those constants lay a story of forces, collisions, and expulsions unfolding over unimaginable distances. Every tiny deviation in the trajectory encoded some aspect of that story. The difficulty in explaining those deviations signaled that parts of the story remained obscure. As the object continued along its outbound leg, the region where its path was best constrained shrank. Observations from multiple observatories, scattered across Earth and space, helped pin down its location from different vantage points. Triangulation enhanced precision, reducing uncertainty ellipses on the sky. The more tightly those ellipses wrapped around the predicted positions, the more clearly the lingering anomalies in the orbit stood out. Precision, in this case, did not soothe. It sharpened the sense that something subtle was missing in the current understanding. The arc carved through space, indifferent to the questions it raised. Gravitation tugged, photons pressed. Any internal sources of thrust did their quiet work. The mathematics traced its path with elegant rigor, while the physicists surrounding those equations wrestled with the lingering mismatch between model and reality. In that mismatch, small but persistent, lay the suggestion that the architecture of interstellar debris might include forms of motion and perhaps forms of matter that had yet to be fully imagined. The first hints that something was wrong came not from the graceful curve of the orbit, but from the invisible arithmetic that underlay every observation. To understand a body in space is to balance its books. Energy in, energy out, forces applied, motion produced. When those ledgers do not reconcile, the discrepancy is not merely a technical issue. It is a sign that some assumption about reality has slipped out of place. Astrophysicists began constructing energy models for the visitor, folding in each fresh measurement. The starting point was simple. Sunlight poured outward, its intensity dropping with distance according to a familiar law. Some fraction of that energy struck the surface of the object, was absorbed, and later re-radiated as heat. Another fraction bounced away as reflected light, which telescopes captured across multiple bands. The brightness and color of this reflected light, along with thermal emissions in the infrared, allowed an initial estimate of how much energy the object was absorbing and how quickly it was losing it again. These calculations yielded surface temperatures that were moderate for a body at its distance from the sunday. Nothing suggested intense heating or dramatic sublimation. If volatile ices existed beneath the outer layer, they were not erupting vigorously into space. Yet, when the same data were used to estimate the magnitude of possible thermal forces, a peculiar tension appeared. The small accelerations inferred from the trajectory seemed too large to be explained by the gentle heating that the thermal model allowed. The discrepancy was subtle, but persistent. If the surface was as inactive as the photometry suggested, outgassing should have been weak. If outgassing was weak, then the non-gravitational acceleration should also have been weak. Instead, the required acceleration, while tiny in absolute terms, sat near the upper edge of what such a quiet surface could plausibly produce. The equations appeared to be asking for hidden energy. One avenue of investigation focused on the internal structure of the body. If pockets of volatile material were trapped beneath a rigid crust, then sunlight might penetrate and warm them without immediately advertising their presence through a visible coma. Internal pressure could slowly build, venting through narrow fissures that produced jets of gas too sparse to create a prominent tail, yet sufficiently focused to impart measurable thrust. In this picture, the energy did not come from nowhere. It was stored slowly and released selectively. To test this possibility, researchers built layered models of the object, assigning different thermal conductivities and porosities to each region. Simulations traced how heat diffused into the interior, how long it lingered, and where it might concentrate. The resulting patterns showed that, under certain combinations of parameters, hidden reservoirs of volatiles could indeed survive and exhale in ways that would escape easy detection. However, matching the precise strength and direction of the inferred acceleration still required the models to be tuned toward more extreme configurations than were typical for known comets. Another route looked outward rather than inward. The environment of the solar system is not uniformly empty. Subtle gradients in the solar wind, small variations in interplanetary magnetic fields, and fluctuations in charged particle densities can all influence the motion of objects to some extent. For large bodies, these effects are negligible. For smaller ones, especially if electrically charged or magnetically responsive, the cumulative forces over long paths can become noticeable. Plasma physicists examined the region of space through which the visitor traveled, using data from heliophysics missions that monitored the charged environment surrounding the Sunday. They mapped out the conditions at the times and locations corresponding to the object's recorded positions. The fields and flows they found were dynamic, but not unusually intense. The calculated forces arising from these conditions were not sufficient to account for the anomalous accelerations unless the object possessed highly unusual electromagnetic properties, such as an extensive, conductive surface or a thin, large-scale charged envelope. Such properties would imply a structure vastly different from the dense, largely neutral aggregates of rock and ice that dominate the catalogue of small bodies. The idea was not discarded, but it demanded explanations for how such a configuration might naturally form in a distant planetary system and survive the journey across interstellar space. For the moment, it remained an intriguing but speculative possibility. As the models grew more complex, a certain unease began to spread through the community of analysts. The equations of motion themselves were not in doubt. Newtonian gravity and its relativistic refinements had proven reliable across countless tests, from falling apples to orbiting spacecraft. The issue lay not in the fundamental form of the laws, but in the input. The unknowns were the object's internal structure, composition, and history. Yet the effort required to coax a coherent explanation from those unknowns felt disproportionate to the modest scale of the observed effects. The sensation was one of laws being stretched, not broken. A guitarist might tighten a string to reach a higher note, feeling the resistance grow as the tension increases. In the same way, the models could be tightened to cover the anomaly, but at the cost of assuming conditions that approached the limits of plausibility. Nature, left to its own devices, usually prefers simpler arrangements. Complexity tends to arise when multiple processes intertwine, or when hidden constraints force systems into awkward configurations. This realization invited a different perspective. Perhaps the visitor was not shaped by a single, dominant process, but by an unusual combination of them. A distant star might have formed a planetary system with a richer mixture of volatile compounds than is typical closer to the Sunday. Gravitational interactions among those planets might have slung smaller bodies into orbits that exposed them to intense tides, internal heating, and partial disruption. Surviving fragments could have fused, cracked, and refrozen into layered constructs, unlike anything seen in the local environment. In this context, the strained energy balance of the object would not reflect a violation of physical law, but instead a testimony to the diversity of planetary histories. The models felt stretched because they were built on assumptions calibrated to the solar system. The anomaly might be a mirror held up to those assumptions, revealing how narrow they had been. A different kind of strain appeared in the statistical expectations. Energy and momentum conservation dictate that ejecting an object into interstellar space requires specific conditions. There must be enough gravitational energy available to accelerate it to escape velocity relative to its home system. In most simulations, this happens during chaotic interactions with giant planets. When thousands of test particles are tracked through such environments, only a fraction gain sufficient energy to escape. Those that do tend to leave with characteristic speed distributions. When the properties of the visitor were compared to these distributions, the mismatch, although not extreme, remained consistently noticeable. It seemed to have started its journey with more kinetic energy than average, as if born from an especially violent interaction. That would be fine if such events were rare and the object itself a unique rarity. Yet the repeated detection of interstellar wanderers within a relatively short observational window suggested that this class of object might be more common than the models allowed. To reconcile this, theorists adjusted initial conditions in their simulations. They increased the prevalence of massive planets, tightened their orbits, and introduced denser clusters of stars that might stir planetary systems more aggressively. With these changes, the rate of ejections rose, making high-energy escapees more frequent. However, such altered conditions had implications for other observable properties of the galaxy, such as the distribution of planets around stars and the overall stability of planetary systems. The tension migrated from one corner of theory to another, never fully disappearing. In quiet discussions, an unsettling possibility was raised. Perhaps the galaxy naturally produces a wider range of planetary architectures than current surveys have revealed. The exoplanet census, impressive as it is still biased towards systems that are easiest to detect. Closely orbiting giants, compact multi-planet arrangements, stars bright enough for detailed follow-up. There may exist entire families of systems whose dynamics favor the production of fast-moving debris, yet whose planets are subtle and difficult to observe with current instruments. If this is true, then 3I divided by Atlas, and objects like it would be emissaries from unseen architectures, carriers of dynamical signatures that betray the existence of planetary realms humans have not yet directly glimpsed. The discomfort in the energy and trajectory models would then be less a sign of broken law, and more an echo of missing context. The feeling that natural laws were being strained, therefore, was as much psychological as mathematical. Equations retained their form. Conservation principles stood unchallenged. Yet the web of assumptions woven around those laws had begun to fray at the edges. Each attempt to explain the object's behavior demanded that something be placed at an extreme, a density, a composition, a planetary configuration, a rate of ejection. One strain might be tolerable. Several, stacked together, whispered of a deeper incompleteness. The visitor, silent and indifferent, simply continued to move, its energy budget written in a language it did not care whether anyone understood. The strain, in truth, rested not on the laws of nature, but on human attempts to compress the variety of cosmic history into a set of comforting expectations. In the gap between those expectations and this particular reality, a new awareness was beginning to grow. Light can touch a surface without ever seeing beneath it, yet the way that light is returned carries tiny hints of what lies hidden. In the case of the interstellar visitor, observers began turning every available instrument toward a single purpose: to coax a buried story out of the photons that brushed against it and came back changed. Each wavelength, each fleeting shimmer, became a clue to what the object was made of and how its outer skin concealed whatever lay below. Spectrographs split the incoming light into delicate bands, like a prism stretching a raindrop into color. Within those bands, certain frequencies dimmed more than others. These dips, narrow and repeated, marked the fingerprints of specific molecules and minerals. By comparing them against libraries of known spectra, scientists could infer which chemical bonds were catching light and how much of each substance might be present. What they found at first appeared reassuring. There were hints of carbon-rich compounds, traces of silicate minerals, and faint signs of frozen volatiles that resembled the familiar ices of water, carbon dioxide, and perhaps more complex organics. These ingredients would not have looked out of place on a cometary nucleus forged in the outer regions of a planetary system. The composition seemed, at a glance, like a chorus already heard. Yet a closer reading uncovered discordant notes. The relative strengths of certain absorption features suggested mixtures that were skewed from the norm. Ratios of carbon to oxygen, nitrogen to carbon, and refractory minerals to volatiles did not quite match the patterns catalogued in the comets and asteroids of the solar system. There was an overabundance of some compounds, a scarcity of others, as if the object had been assembled in a chemical environment with different priorities. More puzzling still was the behavior of the thermal emission. As the object rotated, its surface passed in and out of sunlight, warming and cooling, in a cycle that should have followed predictable thermal physics. Infrared telescopes traced this cycle by measuring the long wavelength glow that radiated from the surface. From these measurements, one can infer how quickly the material stores and releases heat, a quantity known as thermal inertia. The derived thermal inertia did not fit comfortably into existing categories. It suggested a surface that was neither a fluffy blanket of dust, like that of many comets, nor a solid rock slab, like an asteroid. Instead, it hinted at something intermediate, perhaps a crust composed of closely packed grains, fused with ices and organics, forming a kind of composite shell. This was not in itself extraordinary, but when combined with the object's reflective properties, it pushed the interpretation into unfamiliar territory. The albedo, or reflectivity, remained relatively high for a body that had apparently spent ages in deep space. Surfaces exposed for long periods to cosmic rays and micrometeoroid impacts tend to darken as delicate molecules are shattered and soot-like residues accumulate. The visitor, however, clung to a brightness more typical of fresher surfaces, as though something, at some stage, had renewed or protected its outer layer. One hypothesis imagined a cycle of cracking and resurfacing. Internal stresses, perhaps driven by temperature variations or rotational adjustments, could periodically fracture the outer layer, exposing younger material underneath. Over time, this process might maintain a relatively youthful appearance, even as the object traveled through hostile environments. If such resurfacing had occurred relatively recently in cosmic terms, it could explain the higher-than-expected albedo. To test related ideas, researchers analyzed how the brightness changed with phase angle, the geometry between the sun, the object, and the observer. Small bodies often exhibit a surge in brightness when the phase angle becomes very small, a phenomenon known as the opposition effect. The details of this surge reveal information about surface roughness and grain size. When the interstellar visitor was observed at varying phase angles, the resulting pattern suggested a relatively smooth, fine-grained exterior, not the chaotic, boulder-strewn landscape one might expect on an ancient fragment. Polarimetric measurements, which examine the orientation of light waves after they reflect, added yet another layer of nuance. The degree of polarization changed in a way that implied a thin outer coating of organized material, perhaps ices mixed with aligned dust particles. Such a coating would have to be stable enough to survive the journey, but flexible enough to adapt as the object rotated and was warmed from different angles. The image that slowly formed was one of a carefully layered structure, even if no one believed that care had been intentionally applied. Beneath this enigmatic shell, the models required deeper contrasts. To produce the observed rotational light curve and thermal behavior, the internal density distribution had to vary more strongly than in the case of many known comets. Some simulations favored a denser core wrapped in a series of lower density mantles, like nested shells. Others invoked voids and caverns, pockets of emptiness that altered how heat and stress propagated through the interior. Either way, the most natural fits implied an object that was not uniformly mixed, but stratified. The idea of stratification carried implications for its history. Layering of that kind usually arises from processes such as slow accretion, where material falls onto a growing body in stages, or from episodes of internal heating that cause partial melting and refreezing. For an interstellar fragment to possess such complexity, it would likely have experienced a rich sequence of events in its original environment. Perhaps it had formed in a disk where pressure waves sorted particles by size and composition, then later passed through zones of varying radiation and temperature that transformed each layer differently. When the inferred internal structures were compared with the likely stresses of interstellar travel, another puzzle appeared. The voids and gradients should have made the body more vulnerable to fracture. Collisions with even small grains at high relative speeds can chip or shatter fragile aggregates. Yet, this object had survived intact enough to keep its rotation coherent and its spectral signatures stable. It was delicate enough to exaggerate minor forces, but durable enough to endure a journey across light years. Some researchers began to entertain a more radical possibility. If the interior contained complex structures, perhaps these structures were not purely the result of initial formation, but of later reorganization. Under certain conditions, repeated cycles of stress, fracture, and reconsolidation can rearrange material into intricate lattices, creating a kind of natural architecture. Over millions of years, such processes could sculpt a body that appears deceptively simple from the outside, while hosting elaborate, patterned layers within. Within this framework, the missing answers were not signs of hidden engines, but of hidden histories. The outer shell, smooth and reflective, might be the latest chapter in a long story of breaking and healing, heating and cooling, dissolving and crystallizing. Each buried layer would record a different environment, a different phase of stellar and planetary evolution, like the rings inside an ancient tree whose seed had sprouted beneath an alien sky. Attempts were made to estimate the age of these layers indirectly. Exposure to cosmic rays produces specific isotopes over time, and their relative abundances can serve as a kind of clock. While direct sampling was impossible at such distances, subtle shifts in spectral lines hinted at ratios that did not correspond to simple, uninterrupted exposure. Instead, they suggested cycles of shielding and re-exposure. Something in the object's past had periodically covered its surfaces, perhaps with fresh material excavated from its own interior. In the cold halls of analysis, software rendered cutaway diagrams based on these inferences. Color-coded shells represented different densities and compositions. Regions of probable voids were shaded darker, while more compact zones glowed brighter. These visualizations remained speculative, yet they shared a common theme, a complexity that outstripped the simple image of a frozen, undifferentiated chunk wandering between stars. As each new observation arrived, it either confirmed or gently contradicted parts of these pictures, forcing revisions and refinements, yet no single model managed to weave every clue into a seamless tapestry. There always remained a loose thread, a spectral line slightly too strong, a thermal lag slightly too long, a polarization angle slightly too off. The subsurface story stayed just out of reach, glimpsed only in fragments. In that partial sight lay a quiet wonder. Beneath the thin crust of an object barely wide enough to span a small mountain range might lie a record of chemistry, physics, and cosmic weather that no laboratory could hope to reproduce. The thermal shadows and chemical echoes were less like answers and more like voices from distant epochs, speaking in a language that instruments were only beginning to interpret. What they described was not merely a rogue ice rock, but a layered memory of environments far beyond the sun's influence, compressed into a single piece of drifting matter. Resolution is a form of awakening. At low detail, the universe appears simple, softened by distance into points and curves. As focus sharpens, simplicity dissolves and structure emerges. For a long time, the interstellar body remained a point of light, its identity inferred from the rhythm of its brightness and the color of its glow. Then, with deliberate coordination, the instruments around Earth and in orbit began acting together, turning that point into something more like a shape. NASA had gradually extended its reach with an array of telescopes positioned at different vantage points in the solar system. Some orbited Earth, some circled the Sun along slightly offset paths, and a few kept station near stable gravitational waypoints. Alone, each instrument could only glimpse an unresolved speck. Combined through interferometric techniques and careful timing, they formed an effective aperture much larger than any single mirror. Light arriving at each location carried slightly different phase information, tiny variations in wavefront that encoded hints about the structure of the source. Synchronizing these instruments required exquisite precision. Atomic clocks ticked in unison across millions of kilometers. Data packets traveled along radio beams, their timestamps preserved within billionths of a second. Software aligned these streams, reconstructing the wavefront as it would have appeared to a hypothetical telescope spanning a vast region of space. Out of this synthesis, the first coarse images emerged. Initially, the visitor resolved into a blurred spindle, brighter at one end than the other. The aspect ratio suggested an elongated body, but the fuzziness left plenty of room for interpretation. As observation campaigns accumulated more hours of integration, noise fell away, and the contour sharpened. The edges did not look ragged. They met the darkness with a quiet decisiveness, as if the transition from object to vacuum occurred over shorter distances than rough, fractured rock would allow. Subtle features began to appear on the illuminated side. Regions of higher reflectivity glinted like pale islands against a slightly darker background. These patches did not scatter randomly. They seemed to align along gentle arcs and bands, reminiscent of seams or boundaries between materials. On the terminator, where day met night, the silhouette hinted at faceting, with shallow angles that repeated at intervals, interrupting the smooth curve with faint, planar impressions. Careful deconvolution of the images intensified these impressions. Algorithms designed to remove instrumental effects revealed repeating patterns in the reflected light. When the object rotated, certain highlights returned with predictable cadence, as though flat or gently curved panels were catching the sun at specific orientations. These highlights were narrow in time and focused in angle, behavior more typical of specular reflection from smooth surfaces than diffuse scattering from a rubble pile. Ground-based observatories added a complementary perspective. The largest mirrors on Earth, equipped with advanced adaptive optics, used the turbulence of the atmosphere itself as a source of information. By monitoring how starlight twinkled, they adjusted their mirrors in real time to counter the distortions. When pointed at the interstellar visitor, these systems captured rapid sequences of short exposures that, when combined through lucky imaging techniques, yielded moments of exceptional clarity. Across many nights, the best of these frames showed the same unexpected regularities. The limb of the object presented gentle flats and corners, not the infinite variation of a purely eroded surface. Brightness maps constructed from these frames suggested longitudinal zones where reflectivity changed abruptly, like tiles of differing texture. Radar, typically a powerful tool for mapping near-Earth asteroids, could not reach the visitor with meaningful signal strength. The distance was simply too great. Instead, longer wavelength radio observations attempted to detect polarization changes caused by interaction with the object's surface. The faint signals they recovered supported the idea of relatively large, coherent regions rather than a chaotic mix of particle sizes. From these separate strands, a composite picture slowly formed. The interstellar body appeared neither as a perfect cylinder nor as a crude shard. It resembled a tapered structure, thicker in the central region, narrowing toward ends that were blunted rather than pointed. Along its length, the reflectivity suggested bands, perhaps corresponding to layers of differing composition or texture. The overall impression was one of understated symmetry. This symmetry was subtle enough to evade easy description. It did not match the clean axes of a machined object, yet it departed from the usual asymmetry of natural fragments. Some cross-sections appeared slightly oval rather than circular, but retained nearly constant proportions over large stretches. The distribution of bright patches mirrored itself loosely across the midline, as if whatever process shaped the body had acted with a gentle preference for balance. Scientists approached the emerging images with restraint. Resolution at such distances remained limited, and the human brain is notorious for imposing order where little exists. Still, the data did not feel like pure illusion. Quantitative analyses of brightness patterns confirmed that certain angles and separations recurred more often than chance would suggest. Peaks in the spatial frequency domain appeared at specific scales, hinting at repeating structural motifs. One research group explored the possibility that the visitor might be a fragment of a much larger body that had undergone catastrophic disruption. In such an event, tensile stresses and fracture mechanics can produce shards with surprisingly regular geometries. Laboratory experiments on brittle materials, combined with simulations of tidal forces near massive planets, showed that elongated pieces with semi-parallel facets can arise naturally. The regularity in these cases is not intentional, but emerges from the way cracks propagate through stressed solids. Another group considered the role of slow reshaping over time. If the object had once been more irregular, repeated cycles of thermal expansion, contraction, and micro-impacts might have weathered away extreme protrusions, leaving behind a more smoothed and symmetric form. In this scenario, low-energy impacts would preferentially erode sharp corners, while gravitational settling could pull loose material towards stable configurations along the longest axis. A third line of thought invoked rotational dynamics. When a body spins, even slowly, internal mass distribution and external torques can nudge it towards states that minimize energy. Over long timescales, material can migrate, flow, or fracture in ways that align the shape with the spin axis. The visitor's measured rotation period, combined with its apparent elongation, fit within regimes where such evolutionary processes might be significant. Despite these natural explanations, certain details refuse to sit comfortably. The apparent smoothness of some regions, the sharpness of boundaries between bright and dark bands, and the repeated appearance of specific glint angles all pushed the discussion toward more speculative territory. The phrase "too intentional" began to circulate quietly, not as a conclusion, but as a shorthand for the uneasy feeling that the geometry seemed overly tidy. To guard against bias, teams conducted blind analyses. Image processing pipelines were run on synthetic data sets, generated from known irregular shapes, elongated comets, and even human-designed objects, all placed at equivalent distances and blurred to similar resolutions. Analysts, unaware of which inputs had produced which outputs, compared the reconstructed patterns. In many cases, natural reference shapes produced artifacts that resembled regular structures. However, the actual visitor still occupied an outlying position in the distribution, retaining a higher degree of apparent order than most simulated fragments. These exercises did not prove anything definitive. They did, however, highlight how close the imaging had come to the edge of interpretability. At such limits, every pixel carried the weight of multiple hypotheses. Any small correction to calibration, any subtle misstep in deconvolution could tilt conclusions toward or away from extraordinary interpretations. Meanwhile, the object continued to present new aspects as it turned. Small changes in viewing geometry revealed additional hints of structure. On some rotations, the phase of the brightness curve matched the passage of particular features across the visible hemisphere, tying light variations more directly to surface marks than to overall shape. This coupling strengthened the sense that the exterior was not monotonous, but organized. In conference halls and remote calls, high-resolution renderings spun slowly on screens. Models built from the best-fit shape parameters rotated, casting virtual shadows in simulated sunlight. Viewers traced their eyes along the curves, pausing at each apparent edge, each repeating angle. The images possessed an uncanny quality, wavering between sculpture and stone, between design and coincidence. For those steeped in planetary science, the temptation to read too much into these shapes had to be resisted. Nature, given enough time and a wide enough canvas, can reproduce configurations that resemble artifacts without any guiding intention. River valleys can mimic written characters. Crystals can assemble into regular lattices that look engineered. In the same way, a fragment birthed from complex planetary processes might easily acquire a silhouette that hinted at purpose when none existed. Yet even with this caution, the Deep Space Imaging campaign transformed the interstellar visitor from a faint wanderer into a restless question. The structures revealed did not offer a clear answer. They simply sharpened the puzzle. Instead of a featureless lump drifting through the dark, the object now appeared as a delicately shaped relic, carrying on its surface the imprints of forces that had pushed matter toward an improbable equilibrium. The array had done its work, pushing at the boundary of what could be resolved across such vast distances. It provided a glimpse, partial and noisy, of a geometry that refused to settle entirely into any familiar category. In that glimpse, the cosmos hinted that its smaller creations might harbor forms of order that sit somewhere between accident and architecture, daring observers to decide which side of that line they believed they were seeing. Distance usually dulls detail. Objects fade, resolution drops, and the richness of structure collapses back into a single point of light. Yet as the interstellar visitor slipped farther from the inner solar system, something quietly reversed that expectation. Instead of growing simpler in the instruments, its behavior began to acquire new layers of complexity, as if the act of departure were revealing features that had been hidden during the closer pass. The geometry between sun, object, and observers shifted with every passing day. Light no longer struck the surface from the same angles. Shadows migrated. New regions turned toward distant eyes, and the fraction of the illuminated hemisphere visible from Earth and its surrounding satellites changed. Under these evolving conditions, a fresh pattern began to appear in the photometric data. Superimposed on the familiar rhythm of rotation, faint spikes in brightness flickered at irregular intervals, short-lived and sharp. These flashes were too brief to be explained by broad, smooth regions of high reflectivity alone. They hinted at something smaller and more concentrated, facets or structures that only occasionally lined up to catch the sunlight and send it directly toward the detectors. When plotted against the rotational phase, the spikes did not fall in perfectly repeating positions. Instead, they clustered near certain phases, then shifted over time, as if the reflective elements themselves were moving relative to the bulk of the object. At first, the anomalies were tentatively attributed to noise. Distant sources often suffer from sporadic interference, cosmic ray hits, and instrumental quirks. Teams examined the raw frames where the spikes originated, searching for telltale streaks or artifacts. None appeared. The flashes were present in independent instruments, located on different spacecraft and different continents. They were real. A new round of modeling considered the possibility that loose material, perhaps fragments or dust clumps, traveled in close proximity to the main body. If shards had been released during earlier stress events, they might orbit the object or accompany it in a loosely bound swarm. Small pieces with flat surfaces could act like mirrors, producing glints when they crossed particular lines of sight. Their motion would introduce secondary periodicities, complicating the simple rotational signature. Simulations of such swarms showed that even a modest cloud of centimeter to meter-sized fragments could produce the observed behavior, provided they were distributed in specific configurations. Some scenarios placed them in equatorial belts, gently co-orbiting with tiny offsets in speed. Others imagined them as trailing or leading clusters, held only weakly by gravity or by the shared history of ejection velocities. In many of these cases, the combined light curve indeed sprouted sporadic spikes. If such fragments existed, they would also alter the way the object interacted with surrounding space. Dust and debris, no matter how tenuous, scatter sunlight differently than a solid surface. They polarize light in their own characteristic ways and can imprint subtle color changes on the reflected spectrum. Sure enough, as the visitor receded, observers detected a gradual evolution in both color indices and polarization angles that could be interpreted as a growing contribution from a diffuse, unresolved component. This realization prompted a reanalysis of earlier data. Careful subtraction of the best fit reflection from the main body revealed faint residuals that had previously been filed away as noise. When stacked and aligned, these residuals formed a tenuous halo around the reconstructed silhouette. The halo was never bright enough to stand on its own, yet its persistence across many observations supported the idea that the visitor carried with it a cloak of fine material. The existence of such a cloak reshaped theories about the object's recent history. Perhaps during its passage through the outer regions of the solar system, subtle thermal or tidal stresses had peeled off layers of regolith, freeing fragments that now lagged behind or circled lazily. Alternatively, the debris might be much older, a relic of a distant encounter or disruption in its birth system, preserved through the long interstellar journey, like dust clinging to a traveler's coat. As these ideas developed, another, more surprising pattern appeared. Not in direct observations of the object, but in the deep field images captured around it. Many of the telescopes tasked with tracking the visitor did not isolate it exclusively. Their wide fields also collected light from the surrounding sky, which archived data managed to preserve. When analysts began to examine these background fields along the outbound trajectory, they noticed something peculiar. Beyond the main target, faint streaks of motion appeared at brightness levels close to the detection threshold. Individually, these streaks could have been minor asteroids, background comets, or noise. Yet when their directions and speeds were measured, a subset seemed to share a common drift vector, roughly aligned with the path of the interstellar body, though displaced laterally by varying amounts. This alignment caught attention. It suggested that the visitor might not be entirely alone, but perhaps cross-cutting a pre-existing stream of small objects, or even traveling as part of a broader flow. To test this, researchers compared the distribution of these faint movers with models of known populations in the outer solar system. Most matched expectations. A residual group, however, did not fit easily into standard families. Their orbits appeared unusually inclined, their velocities slightly higher than typical for local debris. The possibility arose that these faint companions were not native at all, but interstellar fragments following similar galactic trajectories. If so, 3I, divided by Atlas, was less an isolated traveler and more a comparatively prominent marker within a diffuse procession of matter. The detection of such a procession would imply that the solar system was currently passing through a region of space enriched in debris, perhaps the extended tail of some ancient disruption far beyond sight. This interpretation remained tentative. The signal was weak, the statistics delicate. Still, it encouraged mission planners to widen their gaze. Instead of tracking a single object, They began designing search strategies along the outbound vector, combing its wake for additional fragments. New surveys were configured to stare at the region into which the visitor was moving, rather than only where it presently was, hoping to catch further hints of a stream. As attention shifted outward, instruments sensitive to other forms of radiation added their own puzzling notes. High-energy detectors looking for transient X-ray and gamma-ray events noticed no direct emission from the object itself, as expected. Yet, on 2 occasions, they recorded slight enhancements in scattered background signals that appeared correlated with the line of sight toward the visitor's general path. These enhancements were barely significant, hovering near the edge of statistical reliability. Some dismissed them as coincidence. Others wondered if larger, unseen structures of dust and gas, perhaps aligned with the same galactic direction, were contributing additional scattering. The deep space scans, initially aimed squarely at the interstellar body, now began to reveal a larger context. Its presence drew the eye, but the surroundings whispered of a more extensive architecture, faint and wide, that might stretch far beyond the immediate vicinity. In the same way that a bright lantern reveals dust motes in a dark room, the concentrated scrutiny illuminated subtle motions and structures that had long drifted unnoticed. All of this fed back into revised interpretations of the object's own nature. If it traveled within or near a stream of similar fragments, then its peculiar properties might not be entirely unique. The strained energy balances, the layered interior, the smooth yet banded exterior, and the trailing debris halo could all be variations on a broader class of bodies forged in related environments. The anomaly would then shift from being a single outlier to being the first well-observed representative of an unseen population. Yet such a reframing did not reduce the mystery. It magnified it. An entire cascade of questions unfolded. What kind of event could scatter so many interstellar fragments along similar trajectories, yet leave no bright remnant star cluster or obvious parent structure in current surveys? How long had such streams been crisscrossing the galaxy? And how often had they threaded through the regions of space occupied by the Sun? Had other such streams passed by in eras when no instruments watched, leaving no trace in human records? In the control rooms and data centers where these questions were pondered, the mood took on a new texture. Interest in the solitary visitor evolved into curiosity about its invisible kin and the larger web they might outline. Charts of the sky were redrawn, accenting not only the canonical constellations and planetary paths, but also speculative lines where interstellar matter might have brushed past in ages gone. The interstellar body, receding into fainter magnitudes, had not faded into irrelevance. Instead, it had opened a conceptual corridor into the deeper structure of the galaxy, pointing toward vast, tenuous geometries of debris and dust that might span dozens of light years. Its glints and halos, its faint companions, all suggested that what had entered the solar system was less a solitary stone and more a luminous bead on an almost invisible thread. In following that thread with instruments and imagination, observers found the mystery not narrowing to a solution, but expanding into an even larger question about how the galaxy keeps its quiet record of broken worlds. In every age of astronomy, there comes a moment when data ceases to guide a single narrative, and instead branches into several. The interstellar visitor reached that point quietly, through a slow accumulation of measurements that refused to converge on a single, simple story. In meeting rooms lit by muted screens, and in late-night calls across time zones, the object turned from a shared puzzle into a map of differing convictions. Theories began to cluster. Each cluster had its own gravity. The most conservative interpretation held that the body was, at its core, a stranger that still belonged within the broad family of comets. Advocates of this view pointed to its mixed composition, its modest volatiles, its layered interior. In their models, the visitor originated in the distant outskirts of a planetary system rich in ices. Perturbations from giant planets and passing stars eventually ejected it into interstellar space. Over eons, radiation and micrometeoroid impacts stripped away its more fragile elements, leaving behind a hardened nucleus. Under this view, the object's elongation, smooth belts, and subtle non-gravitational forces were simply the extreme end of natural variation. In a universe that has had billions of years to experiment, unlikely combinations are not only possible, but inevitable somewhere. The apparent regularities in shape and reflectivity were attributed to selective survival. Bodies with certain structures might persist longer in interstellar space, biasing what observers eventually see. A second camp found that explanation insufficiently rich. For them, the key lay in the chemical and structural signatures that hinted at a more specific origin, the fractured crust of a once larger world. They imagined a distant planet, something like Pluto or Triton, cloaked in exotic ices of nitrogen, methane, or carbon monoxide. Over time, impacts and internal heating would crack this crust into slabs. In a catastrophic event, perhaps involving giant planet migration or stellar flybys, some of these slabs could be thrown clear of the system. Fragments of such frozen surfaces possess unusual properties. Nitrogen ice, for example, is brighter and more volatile than water ice, and can sublimate even under moderate warming, supplying thrust with minimal dust production. A shard of this material could account for the high reflectivity, the non-gravitational accelerations, and the peculiar thermal behavior. Proponents modeled blocks of nitrogen and related ices subjected to interstellar radiation, showing that they could retain brightness longer than mixed compositions, while gradually reshaping into elongated forms through preferential erosion. Critics questioned whether enough nitrogen-rich worlds existed to supply a measurable population of such shards. They pointed to the relative rarity of known bodies with similar chemistry, and asked whether this scenario solved one improbability by creating another. Yet the idea persisted, because it connected the visitor to the death of distant frozen landscapes, turning a single object into evidence for an entire class of planetary surfaces far from the Sunday. A third line of thought approached the puzzle from a dynamical rather than chemical angle. In this view, the shape and internal layering of the visitor were the scars of violent tides. A small body that passes close to a massive planet or star can be stretched, fractured, and reassembled by gravitational forces. Simulations of such encounters show rubble piles pulled into strings of fragments, then recombined into elongated aggregates. In some cases, the final products settle into rotating bodies with quasi-symmetric forms and stratified interiors. Advocates of tidal sculpting argued that the visitor's gentle symmetry and possible companion fragments were signatures of such a history. Perhaps a primordial body had once skimmed close to a gas giant, been torn into a train of pieces, and then scattered outward. In this scenario, the interstellar fragment would be one survivor of a catastrophe that shredded others, leaving streams of debris like the faint streaks some telescopes hinted at along its path. Skeptics countered that while tidal forces can indeed generate elongated shapes, they typically also produce strongly chaotic spin states and highly irregular mass distributions. The observed rotational regularity seemed at odds with a violently assembled rubble pile, unless subsequent processes had significantly damped and reshaped it. This tension kept the tidal hypothesis in active debate, with new simulations trying to identify combinations of parameters that could reconcile the models with the measured behavior. A fourth perspective focused on the physics of aggregation at very low densities. In dusty disks around young stars, particles can cluster into fractal structures, fluffy as cosmic ash. If such structures were later compacted by pressure waves, shocks, or moderate heating, they might produce composite solids with internal pore networks and intricate layering. The visitor, in this vision, was less a broken piece and more a preserved template of early planet formation, never fully processed into a conventional planetesimal. Supporters of this idea highlighted the unusual thermal inertia and polarization signatures, which seemed consistent with nested porosities and complex internal voids. They argued that an object formed in a dense, turbulent nebula might retain a memory of that environment in its architecture. This would elevate the visitor to a rare sample of primordial construction, an echo of the stage between dust and world. Others pointed out that such delicate structures would be vulnerable in interstellar space. Collisions, radiation, and repeated thermal cycling would likely collapse their porosity and erase their fractal character over vast timescales. To survive in such a state, The object would either need a protective shell thicker than inferred or a shorter journey than assumed. Both requirements strained the models, but not so much that they could be dismissed outright. As these physically grounded scenarios continued to evolve, a quieter, more controversial set of ideas floated at the periphery of discussion. A small number of researchers, constrained by the same observations, asked whether the apparent thinness, high area to mass ratio, and organized surface regions might resemble the properties of a large, damaged sail or shell. They did not claim that the object was an artifact. Rather, they noted that if one were to design a structure to harness radiation pressure for propulsion, some of the measured parameters would not be entirely out of place. Most of the community treated such comparisons with caution. The history of astronomy includes many episodes where unusual phenomena were prematurely attributed to intentional agency, only to be later explained by natural processes once data improved. The lesson of those stories was clear. Extraordinary claims demand not only suggestive patterns, but robust, independent lines of evidence. Still, the mere fact that the data overlapped even partially with engineered expectations added a charged undercurrent to certain conversations. In practice, this undercurrent manifested as a commitment to designing tests. If a thin, high reflectivity structure were present, it would respond to radiation pressure in ways that differ from bulk solids. Minute changes in acceleration with distance from the sun, orientation relative to the light, or spectral distribution of illumination could reveal such distinctions. Analysts began to devise observational strategies that, while agnostic about origin, were sensitive to these fine differences. The effect of these competing theories on the scientific community was not simply intellectual, it was emotional. Each hypothesis carried with it a different vision of the galaxy. The cometary interpretation painted a universe where planetary systems share a common messy blueprint and interstellar visitors are familiar wanderers wearing foreign dust. The nitrogen shard scenario conjured images of shattered frozen plains, their fragments drifting as long-lived relics of distant surface weather. The tidal fragment view emphasized violence, close encounters turning solid worlds into threads of debris. The fractal aggregate model offered a glimpse into the earliest stages of planet formation, preserved against the odds. Beneath them all, the more speculative comparisons to sails or shells whispered of possibilities that stretched well beyond the current scope of observation. Even if most researchers saw these ideas as unlikely, the very act of acknowledging them forced a sharpening of natural explanations. Every conservative model had to work harder, be more precise, more predictive, to stand firm against the allure of intentional narratives. Conferences and workshops became stages where these visions were presented, tested, and challenged. Slides displayed curves of brightness and temperature, side by side with simulations of tidal disintegration or volatile sublimation. Animated renderings showed hypothetical parent systems with distant planets and perturbed belts, their debris fields evolving into clouds of interstellar shrapnel. Each speaker traced a thread from some corner of astrophysical theory to the specific signatures recorded by telescopes. Questions from the audience often reached beyond the immediate models. What do these scenarios imply about the frequency of similar objects? How might they bias the types of interstellar bodies that are easiest to detect? Do they predict additional observables, perhaps in radio or high-energy bands, that could break the degeneracy between explanations? In answering, researchers revealed not only the strengths of their theories, but also the gaps where assumptions still stood in for evidence. Through this process, the visitor served as a mirror. It reflected back the limits of current understanding, the preferences of different schools of thought, and the ways in which prior discoveries shaped expectations. Those who favored simplicity gravitated toward explanations that required the fewest new ingredients. Those drawn to the galaxy's wilder possibilities leaned into models that embraced rarity and extremity. No single theory managed to claim victory. Instead, a spectrum of possibilities crystallized, from the mundane to the extraordinary, all anchored to the same set of measurements. The room, in a sense, split not because data disagreed, but because the data were rich enough to support several coherent stories. The object had become a crossroads where multiple visions of cosmic history intersected, each plausible, none yet proven, each inviting a different future observation to decide its fate. Speculation does not arrive with fanfare. It begins as a hesitation at the end of a sentence, a pause after the last known explanation has been carefully presented. In that pause, silence fills with possibility. Around the interstellar visitor, that silence slowly thickened until certain questions, once spoken only in private, began to find their way into more public rooms. The starting point for these questions lay in a simple observation. Several parameter sets that best fit the data resembled designs that had been imagined for large-scale sails and shells. Thin structures of high reflectivity, broad surfaces with low mass, geometries that interacted with radiation pressure in predictable ways. Engineers who specialized in advanced propulsion noticed the parallels immediately. On whiteboards filled with equations and concept sketches, they had long drawn diagrams of light-driven craft that could drift between stars with no fuel except starlight. Now, some of those diagrams echoed in the numbers extracted from a distant drifting point. This resonance did not prove anything. Nature is capable of producing thin sheets, layered crusts, and elongated fragments. Yet the overlap between imagined devices and inferred properties introduced a new axis of interpretation. When specialists in sail dynamics examined the object's slight non-gravitational accelerations, they found that, within uncertainties, they matched what a partially damaged, slowly tumbling reflective membrane of certain dimensions might experience near the sunday. These analyses were careful not to jump to conclusions. Instead of naming intentions, they focused on physical behavior. If a structure were thin, how would its acceleration change with distance from the sun compared to a dense solid? How would its rotation evolve under the combined influence of radiation pressure, thermal re-emission, and tiny torques from uneven illumination? Could a fractured sail, riddled with tears and folds, present an external signature similar to that already recorded? Numerical experiments produced diverse outcomes. Some configurations disintegrated quickly, spinning into instability. Others settled into gentle, long-lived tumbling states that matched certain aspects of the observed light curve. In these models, the structure was not pristine. Edges were curled, segments overlapped, and masses were distributed unevenly. Under such conditions, specular glints could occur at irregular intervals, and small fluctuations in acceleration could arise without obvious accompanying changes in brightness. Alongside these simulations, analysts explored purely natural analogues. They modeled slabs of ice and rock shaved thin by erosion, fragments of layered crust peeled away from larger bodies, and aggregates of dust and frozen gas that had compacted into plate-like forms. Some of these natural structures produced similar dynamical signatures. The same codes that had been used to examine sail candidates could, with altered parameters, describe delicate natural forms that responded strongly to light. This dual applicability highlighted the central difficulty. Observers were not confronting a pattern that screamed one origin over another. Instead, they faced a pattern that sat at a junction where natural and hypothetical engineered shapes met, both able to inhabit the same region of parameter space. The object had become a test of how humanity handles ambiguity when familiar explanations share a border with more radical possibilities. Within scientific circles, a quiet divide opened along lines of temperament as much as expertise. Some researchers insisted that, in the absence of incontrovertible evidence for design, the responsible stance was to treat all sail-like behavior as a probe of extreme natural structures. Others argued that, since the galaxy is old and potentially fertile, it would be intellectually incomplete not to at least frame the data in ways that could, in principle, reveal artificial signatures if they existed. This latter attitude did not proclaim the visitor a constructed device. Instead, it sought to articulate falsifiable tests. If a structure were engineered, what patterns might distinguish it from even the most exotic natural forms? Regular modulations in spin that indicated control, specific alignments between rotation axes and trajectories, unusual spectral lines associated with manufactured materials. With these questions in mind, teams proposed observational campaigns that would push instruments to their limits. Precision measurements of tiny changes in rotation period could reveal non-dissipative corrections inconsistent with passive dynamics. Extremely sensitive spectroscopy might detect unusual reflective coatings or absorption features not easily produced by known minerals and ices. Long-duration monitoring of acceleration could check whether the object's response to varying solar flux followed the simple quadratic dependence expected of a purely physical sail, or deviated in ways that hinted at active modulation. Time, however, was a relentless constraint. As the visitor receded, its brightness slipped toward the edge of detectability. Extracting fine details from its behavior became more difficult with every passing week. Planned tests had to be triaged. Only a subset could be executed before the signal faded into the background. It was as if a question had been posed, and then slowly walked out of earshot, while the listeners debated which part of it to answer first. Beyond the observatories, the story of possible sail-like behavior captured imaginations. Public conversations, fueled by condensed summaries and speculative headlines, often leaped further than the cautious language of technical reports. Words like probe, artifact, and visitor acquired connotations that reached beyond their neutral meanings. For many, the idea that a structure from another civilization might drift through the solar system carried an emotional charge out of proportion to the actual evidence. Scientists found themselves in a delicate position. On one side was the obligation to correct overstatements, to remind audiences of uncertainties and alternative explanations. On the other was an awareness that the very act of asking whether something might be artificial had value, if framed correctly. It required humanity to examine its assumptions about uniqueness, about what signs of technology might look like across light years, and about how to recognize unfamiliar forms of order. In conversations that avoided microphones and cameras, some researchers spoke more freely about this psychological dimension. They noted how the possibility of encountering evidence of other minds had long haunted astrophysics, from early radio searches to careful analyses of stellar dimming. Most such efforts had produced null results, or subtle signals best explained by ordinary phenomena. This history had cultivated a habit of skepticism, a reflexive leaning toward natural causes. It also left behind a residue of poignant curiosity, a sense that the cosmos might remain silent even if it were inhabited. The interstellar body became a focal point for that curiosity, precisely because it resided in a region of interpretive uncertainty. It was neither clearly natural nor convincingly artificial. It was a canvas on which hopes and caution painted their respective colors. For some, this served as a reminder that the universe does not owe clarity. For others, it was a prompt to design future instruments and surveys with this ambiguity in mind, so that the next object might be examined with greater discriminatory power. Speculation at this edge had another, subtler consequence. It encouraged reflection on what human technologies might someday look like to distant observers. If an advanced civilization elsewhere saw the slender arcs of spacecraft or the shimmering squares of orbital sails deployed around the sun, how would they classify them? As comets with unusual albedos? As transient dust sheets? Would they, too, argue over natural versus artificial interpretations based on limited data and biased expectations? In this mirrored scenario, the current moment gained a kind of humility. Observers realized that they might be in precisely the same position as any distant watchers trying to interpret human activity without context. The visitor, then, was less a suspect artifact and more a prompt to consider perspective. It invited a new discipline of thinking, a readiness to entertain multiple ontologies without collapsing too quickly into certainty. As the debates unfolded, a consensus slowly formed around a modest but profound point. Whether or not the interstellar object bore any trace of intentional construction, it had successfully expanded the space of serious scientific conversation. It had made it acceptable, within rigorous frameworks, to define and test criteria that might someday distinguish natural relics from technological ones, should such a distinction ever become necessary. In that sense, the object acted as a rehearsal. It allowed humanity to practice how to respond to an ambiguous messenger, how to balance wonder with restraint, and how to build instruments that do not presuppose the answers they seek. Some called this a preparation for encounters that may never come. Others saw it as an inevitable step in the evolution of a species that has finally begun to look outward with both curiosity and discipline. At the edge of sense, where hard data thins and imagination begins to fill the gaps, the interstellar visitor occupied a fragile space. It neither confirmed nor denied the existence of distant craftsmen. Instead, it held up a quiet lantern to the ways in which minds confront the unknown. It revealed that even a modest fragment, drifting through sunlight, can become a lens through which a civilization examines its own readiness to share the galaxy. Testing began from a simple conviction: if reality appears to misbehave, the fault might lie not in the universe, but in the way it is being measured. To confront that possibility, the instruments gathered around the interstellar body were tuned and retuned, as if an orchestra repeatedly adjusting itself to a strange new score. Every frequency band that human technology could access was invited to participate. In visible light, the visitor had already revealed its fickle rhythm of brightness, its slow tumbling and sudden glints. Now the focus shifted to time-resolved spectroscopy. Instead of averaging its light over long exposures, observers sliced the spectrum into finer intervals, capturing how color and line features evolved as different facets rolled into view. Arrays of detectors dispersed the incoming photons into rainbows, then stacked successive rainbows into a moving picture, each frame marked with the exact phase of rotation. This effort exposed delicate changes. At certain moments, absorption features associated with volatile ices deepened, as if fresh material were peeking out from beneath the crust. At other phases, reflective signatures from silicates and complex organics dominated. The pattern suggested patches of varying composition distributed across the surface, each contributing differently as the body turned. The light curves ceased to be a simple brightness plot and began to resemble a choir of overlapping voices, each with its own spectral timbre. Infrared instruments extended the view into warmth. Telescopes cooled to near absolute zero listened for the faint thermal whisper of the object as it absorbed sunlight and re-radiated energy. By comparing the infrared flux with the reflected visible light, analysts traced how efficiently different regions converted illumination into heat. Anomalies emerged there as well. Zones that appeared bright in reflected light sometimes glowed less warmly than expected, hinting at materials with unusual emissivities or buried structures that redirected heat inward. Ultraviolet observations, sensitive to the more energetic photons, played a quieter role. Most of the time, the visitor appeared subdued at these wavelengths, consistent with a surface darkened by exposure to harsh radiation. Yet on rare occasions, modest enhancements appeared, localized in both time and spectral width. They hinted at fleeting events, perhaps small outbursts of gas or the sputtering of charged particles from freshly fractured areas. Further outward, along the electromagnetic spectrum, radio telescopes listened for any sign of coherent emission. The expectation was that there would be none. Rocks and ice do not naturally broadcast in narrow bands. The arrays found no signals that resembled transmissions. However, they did detect a faint, broad continuum arising from the scattering of solar radio noise off the object and its possible dust halo. The way this scattered radiation varied with time added another constraint on the distribution and size of nearby fragments. Polarimetry provided a different kind of test. By measuring the orientation of the electric field in the reflected light across multiple wavelengths, scientists could infer the microstructure of the surface and any surrounding material. The polarization curve as a function of phase angle and color did not match any single known template. Instead, it resembled a blend of signatures. Fine grains aligned along subtle planes, mixed with larger, smoother patches that reflected light in a more ordered fashion. These complex patterns demanded models that combined both rough and unexpectedly coherent structures. While the photons yielded their stories, another tier of analysis concerned motion itself. Precision astrometry, the measurement of tiny shifts in position against the distant star field, reached for the micro-arcsecond level. Multiple observatories at widely separated locations recorded the visitor's apparent position within minutes of one another. Accounting for parallax, atmospheric refraction, and instrumental distortions, the data were merged into a trajectory that traced the object's arc through space with extraordinary delicacy. Into these calculations, relativistic corrections were folded with equal care. Light travel time delays ensured that each observation represented the object not where it was in that moment, but where it had been minutes or hours earlier. The gravitational potential of the Sun and planets bent and slowed the light slightly, imposing the Shapiro delay and minute deflections that had to be removed. The observers, in effect, peeled away the curvature of spacetime itself to reveal the path within it. Once these corrections were applied, the remaining deviations between predicted and observed positions took on heightened significance. Any residual acceleration could no longer be blamed on neglected relativistic effects. The models showed that general relativity and classical gravity alone could not generate the measured, non-gravitational drift. The anomaly remained, standing out more starkly once the subtle warping of spacetime had been accounted for. Some theorists use this as an opportunity to probe alternatives. Modified gravity frameworks, which adjust the behavior of gravitation at low accelerations, were briefly tested against the data. If the force law were different at the fringes of the system, perhaps the visitor's motion could help reveal that difference. Calculations, however, showed that such modifications would also affect the trajectories of planets and spacecraft in ways that were not observed. The interstellar body, oddly distinctive as it was, could not easily be turned into evidence for a fundamental revision of gravity without disturbing many other successfully modeled motions. Attention turned instead to the interplay between shape, spin, and radiation. Detailed light curve inversion techniques took center stage. These methods treated the object as an unknown three-dimensional shape, covered with materials of varying reflectivity, then searched for combinations that reproduced the observed brightness at all recorded phases and geometries. The resulting solutions were probabilistic clouds rather than single sculptures, but they shared certain traits: elongated forms, smoother than average surfaces, and localized zones that consistently produced sharp peaks. To push these inversions further, researchers introduced dynamic elements. They allowed for the possibility of small, co-orbiting fragments, evolving dust halos, and time-varying jets. In some runs, these additions improved the fit to the brightness data but conflicted with the spectral or polarization constraints. In others, imposing too much freedom led to overfitting, where the models matched every nuance of the measurements but lost predictive power. The challenge lay in finding configurations that explained more without inventing more than the data could support. Throughout this process, the object's response to radiation pressure remained a central diagnostic. If the body functioned effectively as a sail, even in a passive, natural sense, its acceleration should track the intensity of sunlight with a clear pattern. Analysts plotted its small deviations from purely gravitational motion against solar distance, solar activity level, and orientation inferred from rotation models. The correlation with distance followed the expected inverse square trend, but with fluctuations superimposed that could be interpreted in multiple ways, as changes in effective area due to tumbling, as shifts in active outgassing regions, or as the repositioning of translucent, possibly sheet-like structures. Because of the visitor's fading brightness, some of the most ambitious tests remained tantalizingly incomplete. High-cadence monitoring of the rotation, intended to catch any signs of deliberate torquing or non-random adjustments, yielded only a slowly drifting period and minor variations that could be attributed to internal redistribution of mass or interactions with the dust environment. No repeating pattern emerged that demanded an external guiding hand. Even the absence of certain features provided information. No strong emission lines associated with industrial alloys appeared in the spectra. No perfectly periodic pulsations announced artificial beacons. No sharp thermal edges indicated embedded power sources. These non-detections gradually pruned the space of wilder speculations, leaving behind a more constrained, if still unusual, range of possibilities. The ensemble of tests painted a picture that was paradoxical in its clarity. Measurements across the spectrum and under the lens of relativity had tightened the object's description to an impressive degree. Researchers knew more about its spin than about many nearer asteroids, more about its surface layering than about several local comets, more about its small accelerations than about some dedicated spacecraft. Yet the more precisely it was characterized, the more stubbornly it resisted assimilation into any single established category. In laboratories and simulation suites, the data became a touchstone for new methods. Algorithms honed on its light curves were later applied to other small bodies, revealing subtleties previously overlooked. Relativistic correction schemes refined during its tracking improved the ephemerides of distant Kuiper belt objects. Spectral fitting routines, tuned to disentangle its blended ice and mineral signals, enhanced the analysis of trans-Neptunian compositions. The attempt to test the impossible, even without fully resolving it, left behind a trail of technical advances. The visitor itself, however, offered no commentary. It did not react when instruments focused more finely upon it, did not change course in response to attention. It simply continued along its predetermined arc, allowing photons to bounce and heat to flow, in accordance with the same indifferent rules that govern every drifting stone. The tests revealed that the anomaly lay not in a breach of those rules, but in an unfamiliar arrangement of their consequences. In that recognition, there was a quiet lesson. When confronted with an object that seems to disobey expectation, the most powerful response is not assertion but measurement, not declaration but listening. By asking light to speak in every possible color, and motion to reveal itself down to the smallest deviations, the observers discovered that the universe had not betrayed its laws. It had instead demonstrated that within those laws, there exist configurations subtle enough to masquerade as impossibilities until they are examined with sufficient care. In the equations that describe motion through space, gravity is not a force in the old sense, but a bending of the stage on which motion occurs. Every mass, from a grain of dust to a star, distorts that stage. Every path is a compromise between inertia and curvature, a line that falls along the contours of space-time. The interstellar visitor followed such a line, a geodesic drawn through the invisible geometry around the Sunday. To understand its journey fully, astronomers had to look not only at where it went, but at the shape of the fabric it crossed. Einstein's framework turned the solar system into more than a collection of orbits. It became a basin in a four-dimensional landscape, with depressions carved by the sun and planets, and subtle undulations from more distant masses. A high-speed traveler cutting past the sun does not simply obey Newtonian attraction, it also responds to the gentle warping of time and distance that general relativity prescribes. For slow-moving bodies, these corrections are tiny. For something arriving with unusual speed from far outside, the corrections begin to matter. Astrophysicists constructed the visitor's path within this curved setting. They imagined spacetime as a field of numbered coordinates, each point holding its own rate of ticking time and its own light cone, opening into the possible futures of any particle that passed. The equations of motion, when written in this language, became statements not about forces, but about how the object traced out the straightest possible line in a geometry that was itself not straight. This perspective reshaped the familiar hyperbola. Instead of a simple conic curve, the trajectory became a slice through the sun's metric, an arc that dipped slightly deeper into the gravitational well than Newtonian predictions would suggest. Light signals sent from Earth to the visitor and back did not travel in a flat void. They skimmed the warped region around the sun, arriving a little later than they would in Euclidean space, their paths bent by small angles that had to be subtracted away. Time dilation entered quietly into the analysis. The clock carried by any hypothetical instrument near the visitor would tick at a slightly different rate than clocks on Earth. At the object's closest approach to the sun, the difference would be small, but measurable in principle. Combined with the high relative velocity, these relativistic shifts meant that, from the perspective of a co-moving frame, the sun's influence unfolded in a subtly altered tempo. The encounter with the solar system, compressed into a brief interlude in the traveler's vast journey, became even shorter in its own proper time. Observers on Earth did not feel these effects directly. They experienced only the integrated result: positions on the sky, frequencies of light, intervals between signals. But the calculations that connected these measurements to physical reality had to account for the fact that light did not move over a flat grid and that time did not pass identically in all places. To reconstruct the visitor's path, software iterated between coordinate systems, transforming between the frame where the sun sat at rest, the frame of Earth in its orbit, and hypothetical frames attached to the moving object itself. In this dance of frames, Einstein's influence was everywhere. The Lorentz transformations that connect different velocities regulated how energy and momentum were computed. The curvature of spacetime determined how much deflection light experienced as it passed near the Sun, affecting the apparent position of the visitor at different points along its arc. Analysts realized that, for such a fast interstellar traveler, neglecting these subtleties would misplace it by enough to blur the already fine line between purely gravitational motion and the extra accelerations that had become so intriguing. At the same time, the object offered a chance to test the geometry that guided it. The solar system had already served as a laboratory for general relativity through Mercury's precessing orbit, the bending of starlight during eclipses, and the timing of signals from spacecraft and pulsars. Now, another test mass, arriving from far outside, traced a unique path through the Sun's influence. If the curvature field deviated in any unexpected way, the mismatch would show up as residual errors in the best relativistic trajectory fits. Researchers extended their models to include contributions not only from the Sun and planets, but from the broader gravitational environment. The Milky Way's mass distribution, dark matter halo, and nearby stars all imprint a faint gradient on local spacetime. Over the length scale of the solar system, this gradient is weak, yet a fast object arriving from interstellar distances carries with it the imprint of that larger field. Its initial velocity and direction encode the history of motion through the galactic potential, just as a stone's flight reveals the slope from which it was thrown. This connection gave the visitor a dual role. On one scale, it was a test particle responding to the Sun's curved field. On a larger scale, it was a messenger from the galactic landscape, its velocity vector a remnant of distant gravitational encounters. By fitting its inbound speed and direction within models of the Milky Way's structure, theorists probed how matter, both luminous and invisible, is distributed in the neighborhood of the solar system. Deviations from expected patterns could, in principle, hint at clumps of dark matter or past passages near unseen stellar remnants. No dramatic departures emerged. The trajectory, once relativistic corrections were included, sat within the envelope projected by existing models. The object's motion through spacetime did not demand new physics. Instead, it reaffirmed that the geometry Einstein described still governed the dance, even when new and exotic shapes took the stage. Yet there was something striking about watching such an abstract theory play out in so concrete a way. Equations written a century earlier, based on the bending of starlight and the ticking of clocks, now guided the interpretation of a lone fragment from another star's realm. Hawking's ideas hovered at the edges of these reflections. His work on black holes had emphasized that spacetime is not merely a static backdrop, but a dynamic arena where horizons, singularities, and quantum effects intersect. Although no black holes lurked near the visitor, the conceptual shift he championed lingered. The object's passage through the Sun's curved field could be viewed as a tiny probe of a far milder, but structurally similar, geometry. In both cases, matter tells spacetime how to curve, and spacetime tells matter how to move. Some theorists extended this analogy into speculative territory. They considered whether the visitor's path might intersect tiny, transient ripples in spacetime produced by distant mergers of compact objects. Gravitational waves from such events pass through the solar system as minute strains, stretching and squeezing space itself by fractions far smaller than an atomic diameter. In principle, a passing object might experience infinitesimal nudges from these waves, though the effects would be far beyond any realistic detection. Still, the thought experiment tied the local encounter to the vast drama of colliding stars and black holes elsewhere in the galaxy. Relativistic thinking also altered how the object's origin was imagined. In a Newtonian picture, one can trace its path backward in time as a simple line through space, eventually intersecting some distant region where an ejection event occurred. In a relativistic context, the past is not just a place, but a structure of intersecting light cones. The true causal history of the visitor includes all events whose light could have reached its formation site before it was expelled, and all massive influences whose curvature shaped the region. The fragment's birth and launch become nodes in a network of causality stretching across both space and time. Visualizations of this network showed nested cones extending from the object's current position back through the evolving galaxy. Supernovae, stellar migrations, and the growth of spiral arms all intersected these cones, each contributing in some small way to the environment that eventually formed the parent body. While this did not pinpoint a specific origin, it framed the object as part of a larger story of galactic evolution rather than an isolated anomaly. Its motion through spacetime was not random, but one thread in a tapestry woven by countless masses and events. In another sense, Einstein's shadow fell on the way observers themselves perceived the encounter. The finite speed of light ensures that every observation is a glimpse into the past. Each spectrum recorded, each position measured, captured the visitor as it was minutes or hours earlier. No instrument ever saw it in the present of its own frame. The object, by the time its photons arrived on Earth, was already somewhere else along its geodesic. This delay introduced a quiet melancholy to the enterprise. Tracking the interstellar fragment became an exercise in chasing ghosts, always following where it had been, never quite reaching where it was. The space between the object's actual position and the last point from which light had departed formed a moving gap that no increase in technology could fully erase. Even at the speed of thought, understanding lagged behind reality by the unavoidable interval set by relativity. Yet within that gap, there was also a kind of grace. The limitation forced a recognition that knowledge of the cosmos is always retrospective, always an act of reconstruction. Einstein's insight, that nothing outruns light, meant that every observation involves decoding messages sent from different times and places. The interstellar traveler was no exception. Its path, through curved spacetime, could be charted only through these delayed signals, each a small confession of where it once had been. As calculations, observations, and theories intersected, a picture emerged that did not overturn fundamental principles, but deepened them. The visitor did not reveal cracks in the structure of spacetime. Instead, it illuminated how rich that structure becomes when even a single unexpected body passes through. It showed that general relativity is not only about massive galaxies or extreme objects, but also about the quiet journeys of modest fragments that feel every contour of the cosmic landscape. There is a particular quiet that exists between galaxies, a silence so deep that it can be described only as absence made visible. In that quiet, matter thins to almost nothing, and yet, in the language of modern cosmology, the void is not empty. It is a volume where the earliest whispers of the universe still linger, carried in faint ripples of density, in thin streams of dark and luminous debris. To look at a lone fragment moving through space is to be confronted with the question of how much of that ancient history it still remembers. Long before any star ignited, the universe existed as a dense, hot fog of particles and radiation. Tiny quantum fluctuations, inflated by expansion, were stretched into seeds of structure. Where density was slightly higher, gravity began its slow work, drawing matter together into filaments, knots, and clouds. Everything that would later become galaxies, stars, planets, and fragments began as subtle variations on an almost perfectly smooth field. Stephen Hawking spent much of his life tracing the implications of that beginning. In his equations, the early universe was not a simple stage, but a dynamic arena where extreme conditions could briefly give rise to exotic objects. Among the possibilities he and others explored were primordial black holes, tiny horizons that may have formed when density fluctuations briefly crossed critical thresholds. If such relics exist, they would drift through the cosmos as invisible anchors, influencing nearby matter without revealing themselves directly. The idea that small black holes might populate the galaxy remains speculative, yet it offers an evocative lens through which to view isolated bodies in space. A fragment of rock or ice moving through interstellar regions does so within a web of gravitational influences that includes not only stars and gas, but any compact dark objects that might lurk unseen. A close passage near one of these relics could subtly alter the fragment's speed and direction, imparting an energy signature that carries the mark of encounters far stranger than the familiar gravity of stars. Even without invoking such extremes, the early universe imposed its character on everything that followed. The relative abundances of light elements, set in the first minutes after the Big Bang, determined which chemical pathways would later dominate. As the first stars formed, lived, and died, they enriched their surroundings with heavier elements, but not uniformly. Regions that hosted more massive stars early on would end up with different chemical fingerprints than quieter neighborhoods. Fragments formed in those regions would carry compositions that subtly trace those early histories. When cosmologists study an object with unusual chemistry, they see not only its immediate parent system but also the deeper lineage of the galaxy. Ratios of certain isotopes can hint at how many generations of stars have lived and died in the material's ancestral clouds. Unusual enrichments or deficits may signal that the fragment condensed from gas that was processed in atypical ways, perhaps near early bursts of star formation or close to energetic events that reshaped local conditions. The interstellar traveler, with its blend of crystalline order and chemical oddities, invites such thinking. If its composition deviates from patterns familiar in one planetary system, it may be because it condensed in a region with a very different stellar history. Perhaps its parent world formed near the edge of a primordial star cluster, where supernovae punched cavities through gas and dust, sculpting pockets of exotic chemistry. In that scenario, the fragment is not merely a shard of a shattered surface, but a relic of an environment that has since dispersed into the broader galactic medium. Hawking's work also emphasized how horizons divide the knowable from the unknowable. In black hole physics, an event horizon marks the boundary beyond which information cannot return. On larger scales, cosmology speaks of particle horizons and cosmological horizons, limits to what can be observed, because light has not had enough time to cross the expanding universe. Small objects drifting through space carry their own, more modest horizons of ignorance. No one can see the full story of what they have experienced, only the traces left in their structure and motion. Viewed this way, the fragment becomes a kind of horizon of memory. Its interior layers record events that no observer can reconstruct in detail. Collisions, heating episodes of slow accretion, tidal stretches, and long passages through cosmic voids are all encoded in the arrangement of its densities and fractures. Each void within it, each abrupt change from one composition to another, is a boundary between eras, much as cosmological horizons, separate epochs in the universe's evolution. Beyond individual objects, there is the question of how debris organizes itself on the largest scales. Gravity draws matter into galaxies and clusters, but it also leaves behind filaments and gaps, rivers of dust and rock that drift between more conspicuous structures. Simulations of galaxy formation show streams of material pulled out by tides, remnants of ancient mergers that stretch for tens of thousands of light years. These streams are faint, almost invisible, yet they form the skeleton of a vast cosmic archaeology. Fragments like the interstellar traveler could be pieces of such streams, long dispersed and diluted, yet still roughly aligned along paths carved in the early life of the galaxy. If one imagines the Milky Way as a city seen from afar, then these streams are the forgotten alleyways and old roads, used less often now, but still guiding the movement of those who remember where they are. A solitary shard passing through the solar neighborhood may have followed such a path for eons, its trajectory not random, but inherited from the tides of long-vanished encounters. Hawking's studies of quantum fields in curved spacetime added another layer to this picture. He showed that even empty space is restless, seething with virtual particles that flicker in and out of existence. Near horizons, this quantum activity can manifest as real radiation, a slow evaporation of black holes that blurs the boundary between nothingness and something. On human scales, the same quantum froth seems remote, yet the idea that the vacuum is never truly empty echoes in the way interstellar space is now understood. Between the stars, the void contains fields, photons, particles, and dark matter, all interacting in subtle ways. Over long times, these interactions can erode, charge, or heat small bodies, even in places where no star shines strongly. A fragment that wanders for billions of years through such regions accumulates that history, not as dramatic scars, but as a gradual reshaping of its microstructure. The smoothness and brightness of certain surfaces, the survival of fragile chemical bonds, the erosion of others, all trace back to the ambient conditions of the void it has crossed. In this sense, the visitor can be imagined as a witness to the quiet processes that rarely demand attention. Cosmic rays, born in distant supernovae and perhaps near black hole jets, endlessly bombard small bodies. Their impacts fracture molecules, alter crystal lattices, and generate new isotopes. Hawking's interest in the interplay of quantum phenomena and gravitation reminds observers that such particles are not mere afterthoughts, but part of the universe's way of redistributing energy and information across vast distances. There is also a more philosophical echo in his work. Hawking often spoke of the universe as a place where boundaries between beginning and end are less clear than intuition suggests. In some of his models, the early universe may have no singular start in time in the ordinary sense, but instead a smooth origin where temporal and spatial dimensions transform into one another. Under this view, questions about before the Big Bang lose their meaning. Transposed to the scale of a single interstellar fragment, a similar ambiguity appears. Where does its story begin? With the first dust grains that gathered in a cooling nebula? With the assembly of its parent world? With the event that tore it free into its own path? Or further back, with the nucleosynthesis in ancient stars that forged its atoms? Each candidate beginning pushes the origin deeper into cosmic history, approaching epochs where the familiar distinction between object and environment blurs. The fragment, then, becomes a small expression of a larger truth, that nothing in the universe is truly isolated. It is a node in networks of cause and effect spreading across time and space. Hawking's equations, used to describe black holes and early cosmology, can be seen as tools for tracing such networks at their most extreme. The interstellar traveler, shaped by forces weaker and less dramatic, still belongs to that same fabric, its path one more geodesic, in a cosmos where even seemingly solitary journeys are entangled with everything else. As it moves through the galactic medium, the fragment threads regions that have been shaped by events too vast and slow for any single observer to witness. It traverses gradients in dark matter density, passes near relics of bursty star formation, skirts the outskirts of ancient clusters that have since dissolved. In its current form, it holds only a condensed record of these experiences, written in layers, fissures, and slight departures from familiar behavior. In contemplating such an object, there is an echo of Hawking's most enduring insight that the universe, at every scale, holds more information than any observer can fully access. Horizons limit what can be known, not as a failure of curiosity, but as a structural feature of reality. The interstellar fragment carries its own horizon of inaccessible detail. Observers can sample its light, reconstruct its motion, model its interior, but they cannot read every line of its past. Yet within what can be known, there is still profound richness. A single piece of matter, small on astronomical scales, can connect present instruments to the physics of the early universe, to the quiet action of the void, to the speculative realms of dark intermediaries and primordial relics. It can serve as a bridge between theories written for black holes and those meant for planets, between the violent brightness of early starbursts and the gentle dimness of a solitary traveler. The decision to pursue the next visitor did not arise from a single meeting or memo. It accumulated quietly, like dust in a beam of light, as simulations, debates, and observations converged on the same conclusion. Encounters with interstellar bodies were not singular miracles, but recurring opportunities. The question shifted from whether they would come again to how prepared a small, evolving civilization wished to be when they did. In planning rooms where mission concepts are born, designers began sketching architectures that assumed a steady trickle of wanderers across the solar frontier. The first element of this new strategy involved seeing farther and faster. Existing survey telescopes, powerful as they were, had been built for broad purposes, cataloguing near-Earth asteroids, mapping distant galaxies, tracing the large-scale structure of the universe. Now, the need arose for a specialized form of vigilance, tuned to the faint, fast-moving signatures of objects that did not belong. Engineers proposed constellations of small telescopes stationed far from Earth, in orbits around the Sun that provided maximal parallax and minimal glare. Each would sweep vast swaths of sky continuously, feeding data into a shared, automated pipeline. Instead of a single pair of eyes, the solar system would possess many, distributed across millions of kilometers, converging their gaze on the subtle streaks that signaled incoming travelers. Machine learning systems, trained not only on known asteroids and comets, but also on simulated interstellar trajectories, would prioritize these faint tracks for rapid follow-up. The second element of the strategy recognized that detection alone was not enough. By the time an interstellar body grew bright enough to attract attention with current instruments, it was often already rushing through the inner system on a path that left little time to send anything after it. The speed required to chase such an object from a standing start near Earth pushed propulsion systems toward their limits. If a physical encounter was ever to be achieved, some form of readiness had to be placed in advance where it mattered. One concept imagined a fleet of dormant interceptors parked in deep space, far from any single planet, at locations chosen for their flexibility. These craft would wait in a state of hibernation, systems powered down to minimal levels, their trajectories carefully arranged so that small course corrections could send them toward a wide range of possible incoming paths. When a new visitor was identified and its orbit estimated, one or more of these silent sentinels could be awakened, their engines ignited to bend their courses toward a rendezvous. Another vision looked to sails instead of rockets. Thin, reflective membranes, once unfurled, could be steered using only light from the sunday. Unlike chemical engines that consume fuel, a sail could, in principle, operate for long durations, gradually building up speed. If deployed early enough and guided toward regions where interstellar objects were likely to appear, such craft could be positioned as agile scouts, able to pivot toward a newly identified target with relatively modest adjustments. Hybrid designs combined the strengths of both approaches. A chemical or electric propulsion stage would handle rapid deployment and major trajectory changes, while a sail would provide sustained fine-tuning and additional acceleration. Small landers, equipped with drills or harpoons, could be attached to these platforms, ready to detach and attempt contact once the main body came within reach. The challenge was not only to arrive, but to arrive gently enough to survive, without knowing in advance how strong or fragile the target would be. Mission planners confronted a fundamental trade-off. The more specific a design became, the more efficient it was for a narrow range of targets, but the less adaptable it would be to the unknown. Interstellar bodies might vary wildly in size, composition, speed, and approach angle. A probe optimized for a volatile rich shard might fail dramatically if it encountered a rocky, rapidly spinning object instead. To address this uncertainty, designers leaned toward modularity, spacecraft built from interchangeable units that could reconfigure themselves in flight, altering their mass distribution, sensor focus, and operational modes in response to updated information. Alongside hardware, a new philosophy of data emerged. Rather than treating each encounter as a separate campaign, scientists began to think in terms of a continuous archive of interstellar traffic. Every detection, even of objects too faint or fast for detailed observation, would be logged with care. Sky position, brightness, motion, and estimated orbital parameters. Over time, this archive could reveal patterns that individual events could not. Clusters of trajectories might point back toward common source regions, hinting at distant planetary systems that regularly shed debris. Statistical distributions of speeds and inclinations could refine models of how material is expelled from different architectures of planets and stars. In this framework, a single close encounter became the bright tip of a much larger iceberg. The value of intercept missions lay not only in the samples they might one day return, but also in the way they calibrated the broader record. A fragment analyzed up close could anchor interpretations of countless others, observed only as faint streaks. Grain size distributions, isotopic ratios, and structural features would link the detailed and the distant, turning anonymous tracks into members of a growing family tree. Ideas for more ambitious experiments emerged as well. Some envisioned using the sun itself as a lens, exploiting its gravity to focus the light from remote targets. A telescope placed at the solar gravitational focus, far behind the sun relative to a chosen line of sight, could magnify distant interstellar bodies crossing that line far more than any conventional mirror. Although such a station would be technologically demanding to establish, it would open a new window on the faintest wanderers, turning even small fragments into resolved sources rather than points of light. Others considered the possibility of seeding the solar system with tiny, passive detectors that required no propulsion at all. Free-flying chips, each carrying miniature cameras and sensors, could be released in dense clusters along likely approach corridors. They would float, barely maneuverable, waiting. If a fast-moving object swept through the cloud, some of these chips might be struck, destroyed, or carried along for a time. Their last transmitted data or altered trajectories would then encode a record of the encounter, like dust motes bearing the imprint of a passing hand. Beyond these technical visions lay a more subtle evolution in mindset. Interstellar visitors had once been imagined as intruders, rare and disruptive. The emerging picture suggested something different, a faint but constant exchange of material among stars, a galactic circulation that the solar system had always been part of, unnoticed. Treating this exchange as a subject of systematic study reframed humanity's place in the galaxy. The solar system was not an isolated island, but a porous node in a larger network of drifting fragments. This shift carried philosophical weight. The possibility that pieces of distant worlds regularly pass through the sun's domain implied that cosmic histories overlap in tangible ways. A shard from a planet formed under another star might carry within it prebiotic chemistry unlike any found locally. Conversely, debris ejected from the solar system in the distant past may by now be passing silently through the realms of other civilizations, if such civilizations exist, offering them their own questions and enigmas. As planners discussed these implications, they faced practical constraints as well. Budgets are finite, launch windows are limited, technologies mature at their own stubborn pace. Not every speculative concept could be pursued, and not every hoped-for mission would receive approval. Yet, even modest developments promised to change the response to future visitors. Slightly larger survey mirrors, more sensitive detectors, improved propulsion stages, and better coordination between agencies would, together, transform what could be done on short notice. The most important preparation, some argued, was not hardware at all, but protocol. Clear procedures for prioritizing targets, allocating telescope time, and triggering mission adaptations would ensure that opportunities were not lost in hesitation or disagreement. International frameworks could define how information about new interstellar detections was shared, how different spacefaring nations could coordinate, and how scientific priorities would be balanced against other uses of observational and launch capacity. In simulation environments, hypothetical visitors appeared one after another, a small, slow object skimming just outside Mars' orbit, a large, dark fragment plunging steeply from the galactic north, a fragile, volatile, rich shard crossing the outer system at high speed. For each, teams rehearsed their response. They chose which instruments would watch, which missions could adjust course, which future launches would need to be accelerated. Through these exercises, possibilities hardened into plans. The pursuit of such preparations carried a quiet aspiration. To intercept an interstellar traveler, to sample it directly, would be to hold in human hands a piece of matter that had once orbited a foreign sunday. It would be a tangible link between planetary systems, a physical letter delivered by gravity and time. Even if no dramatic revelations emerged, the act itself would mark a milestone. A moment when a species confined to one star reached out, not only with light and radio, but with touch, into the shared debris of the galaxy. In the end, the object became small again. On the screens where it had once claimed center stage, it shrank back into a dim point, then into the background of ordinary stars, then into numbers that slowly slipped below detection thresholds. Night after night, the plots grew quieter. Error bars widened. The visitor's presence, which had once shaken equations and imaginations, thinned into a line on a chart that finally trailed off into blankness. Somewhere beyond the reach of those instruments, 3I divided by Atlas continued. It moved in silence, through a region of space that contained no landmarks, no subtle gradients of starlight for human eyes to recognize. Its path curved gently within the galactic field, a long arc stitched together from the gravity of distant suns and the pale haze of unseen matter. There were no markings on the route, yet the fragment followed it with perfect obedience, its speed set by events long past. In control rooms where its data had once filled monitors, other tasks slowly reclaimed attention. New comets rose from the darkness. Exoplanets revealed faint hints of atmospheres. Instruments were recalibrated, software rewritten, missions reconfigured. The visitor's name remained on file servers and in archive directories, a label attached to files that would, from now on, be opened less frequently. The excitement that had once flared around it softened into memory. Yet the quiet it left behind was not the quiet of closure. It was the quiet of an unfinished thought. The analyses had narrowed possibilities, tested theories, and measured properties with remarkable precision, but no single narrative had emerged to bind all the clues. This was not a failure. It was a boundary. The fragment had drawn a line around what the current instruments and methods could reach, and beyond that line, silence remained. For those who had followed its passage most closely, that silence carried a peculiar weight. Astronomers and physicists who had spent months or years watching the faint pattern of its light found themselves returning, in unguarded moments, to simple images, the suggestion of smooth bands on its surface, the strange balance of its motion, the whisper of possible companions in its wake. They knew the data had been parsed, modelled, interrogated from every angle. Still, the sense persisted that something essential about the object remained just beyond articulation, like a word that hovers at the edge of recall. Students entering the field encountered 3I, divided by Atlas, first as a case study. They read about its characteristics in papers and review articles, saw its trajectory drawn cleanly in diagrams, learned how it had tested models of composition and dynamics. To them, it appeared almost straightforward, a neat example of how science grapples with anomalies. Only later, as they traced the chain of assumptions behind each conclusion, did the unresolved corners become visible, the regions where the models strained, the parameters that had to be nudged, the questions that had been acknowledged and then set aside for lack of further evidence. Beyond the technical details, something subtler had changed. The sky itself, viewed through the lens of this interstellar encounter, felt slightly less distant and slightly less static. It no longer seemed like a sealed vault, populated only by objects that belonged to the Sunday. Instead, it began to resemble a crossroads, with paths from other stellar neighborhoods occasionally intersecting the local plane. The constellations, once thought of as patterns pinned firmly to the sphere, became a backdrop for a deeper circulation of material, a slow mingling of histories. In planetariums and observatories open to the public, the story of 3I divided by Atlas took on a quieter, almost meditative tone. Visitors sat under projected stars while narrators spoke of a shard from another system passing through, carrying with it a record of events that no human would ever fully decode. Children stared up and asked where it was now, how far it had gone, whether it would ever return. The answer was always the same. It would not. It would continue outward, until even the memory of the sun's warmth became an imperceptible detail in its long journey. For some, this image was unsettling. There is a certain comfort in believing that mysteries present themselves, yield their secrets, and then conclude. The interstellar fragment refused to participate in that kind of narrative. It arrived without invitation, stayed briefly within reach of detailed attention, and then departed still wrapped in partial secrecy. It behaved like the universe itself, generous with hints, stingy with instruction, yet there was also a strange tenderness in the idea of its ongoing motion. By now, the fragment was passing into regions where the sun was just one star among many, a single point in a crowded sky. The faint dust halo, if it still existed, would be illuminated by new constellations from new angles. If there were any small fragments trailing it, they would drift together through changing stellar neighborhoods, bound not by intention, but by a shared trajectory through the galactic web. On Earth, the only trace left was knowledge. Not knowledge in the sense of a solved puzzle, but in the sense of newly drawn outlines of ignorance. Certain sorts of interstellar debris could now be described with more nuance than before. Certain assumptions about planetary systems and galactic structure had been tightened or relaxed. Instruments had been sharpened, data pipelines refined, methods tested and improved. The next visitor would be met by a different, more prepared gaze. In the quiet of late hours, Some of the scientists who had worked on the fragment's data found themselves thinking not about equations but about scale. A small object, perhaps only a few hundred meters across, had passed through a system that holds planets millions of times larger, all orbiting a star that outshines it by unimaginable factors. Yet for a brief period, human attention had pivoted toward that tiny body with intense concentration. It had become, for them, the center of the universe. That disproportion felt meaningful. It spoke to a peculiar human capacity, the ability to invest vast emotional and intellectual energy in something that is, on cosmic scales, almost vanishingly small. A point of light on a plot could pull entire teams into sleepless effort, because behind that point lay the possibility of understanding something new about reality itself. No galaxy, however grand, is immune to being temporarily overshadowed by a grain of matter, if that grain carries the right kind of question. The question that 3I divided by Atlas left behind had no single form. For some, it was, how many such objects exist, and what does their distribution say about the unseen architectures of distant suns? For others, it was, how strange can natural processes become before they are mistaken for purpose? For still others, it was less about physics and more about belonging. What does it mean to live in a galaxy where pieces of foreign worlds pass by, indifferent to the life that watches them? In each case, the question pointed forward. Plans for new surveys and intercept missions were not acts of closure, but acts of invitation, addressed to visitors not yet seen. The hope was simple and radical at once. That, by paying close enough attention to the debris that drifts through the solar system, humanity might read traces of events that occurred under other stars, in other times, under conditions that could never be recreated locally. The fragment itself would never know it had been noticed. It had no instruments to record the curious focus turned upon it, no capacity to register the brief flare of attention from a small, inhabited planet. To its inert structure, the solar encounter was just another gradient in light and gravity, another region of space to traverse. If it endured long enough, it might one day pass near other stars, other worlds, perhaps other minds. Or it might wander forever in darkness, unremarked upon again. From the perspective of that indifferent journey, human questions might seem fragile, almost weightless, yet they had consequences. The attempt to understand 3I divided by Atlas had reshaped instruments, refined theories, altered how the sky was mapped, and deepened a sense of living within a dynamic galaxy rather than at its edge. A small fragment had pulled on a long chain of curiosity, and the chain had moved. Somewhere in the thin, cold regions between stars, the object travelled on, carrying inside its quiet mass a history that no observer would ever read in full. Yet, its passage through the solar system left behind a different kind of record, written not in rock or ice, but in thought, a realization that the universe is not only composed of distant lights and local orbits, but also of messengers that cross the boundaries between systems, bringing with them evidence that worlds break, matter drifts, and stories intermingle. In that realization, there was a soft kind of hope. If a fragment from a foreign sun can be seen, measured, and contemplated from this small world, then the separation between stellar neighborhoods is not absolute. The galaxy, for all its enormity, allows its pieces to touch, if only briefly, and in those brief contacts, beings who look upward can find not answers, but an invitation to keep looking. Epilogue. Night settles over the planet. One more rotation traced beneath a sky that now carries, in addition to its familiar constellations, a quiet awareness. Somewhere beyond the faintest stars visible to the eye, beyond the reach of the longest radio dishes and the most patient mirrors, a small body continues to glide through the dark. No instrument follows it now. No telescope is centered on its coordinates. Yet its existence has already done its work. In the stillness of observatories after their domes have closed, computers hum softly, preserving archives of its light. Drives hold spectra where its chemical fingerprints lie dormant. Code remembers how its motion deviated slightly from expectation. These are the faint echoes of the encounter, traces of a dialogue with a visitor that never spoke, but that changed the questions being asked. Far from these rooms, a child might look up and imagine that somewhere among the stars, A piece of another world is passing by, unseen. The child does not know the equations or the arguments, but senses something true, that the universe is not a static painting, but a place of journeys. Some journeys end on surfaces, in seas or on plains. Others never arrive anywhere at all, but wander without destination, bearing only the marks of what has happened to them. The story of 3i, divided by Atlas, belongs to this second kind. It is a narrative without a climax, a passage without a final revelation. Its power lies in the way it leaves things open. There are more fragments out there, more shards from broken systems, more relics from long-dissolved arrangements of stars and planets. Each one moves along its own curve through the galaxy, indifferent to who might be watching, yet available, in principle, to any eye that can find it. For a species that has only recently learned to see beyond its own sky, this is both humbling and consoling. Humbling because it reveals how partial every understanding must be. Consoling because it suggests that the cosmos will not run out of mysteries. Long after this particular fragment has vanished into uncharted depths, others will come, each bringing a slightly different challenge, each offering a slightly different glimpse into the vast, intertwined history of matter and light. Some nights will be cloudy, some detectors will fail, some missions will never leave the ground, yet the patient turning of the planet continues beneath a sky that, in its silence, contains a promise, that there will always be more to find than can be found, more to question than can be answered. The passing of a single interstellar visitor is just one moment in that open-ended conversation. As the world slips deeper into darkness and its cities dim, the thought of a small shard drifting through the galactic night can carry a curious comfort. It is a reminder that even in the deepest distances, motion persists, stories unfold, and connections are possible. The fragment will never know it was seen. The galaxy will not mark the event. Yet for those who turned their instruments and imaginations toward it, the encounter has become part of an inner landscape, a quiet place where wonder and uncertainty meet. Sleep comes, eventually, to most who watched those data streams. The sky remains where it was, patient and unconcerned. Somewhere within it, beyond the reach of any present eye, 3i divided by Atlas travels on, a solitary traveller, in a universe that is anything but empty. Its precise course no longer matters. What matters is the space it opened in human thought, a space where the next unknown can one day arrive and find minds already waiting. End of script. Sweet dreams.